Again, a very good morning to all of you. I mean, it feels very great. I'm delighted to see so many of you turning up today for this event that we have put together. Uh, the theme, of course, has generated some interest within the people, within the audience. It's also great to see some young students from Khalifa University joining this event. Uh, I think they are the ones who need to be aware of this new market, new energy where the world is heading towards. On behalf of SUT Middle East, I extend a warm welcome to all of you. Energy supply, affordability, and sustainability, being termed as energy trilemma today, has lately become more relevant topic than ever. In this direction, the emergence of new energies, technologies, the expanded use of renewables, the energy sources, hydrogen technologies, CCS, energy storage, electrification, etc., are addressing the problems of energy supply adequacy, the climate change, and the environmental protection. Now, with little over 2.5 months remaining to COP28, which will be held in Expo City, UAE. Now, I would presume all of us are aware what COP is. It is the largest gathering of the global leaders who converge at one place and with a common goal and common agenda of climate resilience. It is the perfect time for all of us to come together and discuss how industry can share knowledge, experience, and further look to collaborate and develop solutions for accelerating the energy transition. That is what is needed today. The theme of today's event is Road to COP28, Offshore Renewables and New Energies, where the speakers will provide us an overview of their offshore technologies that they are developing in the areas of CCUS, offshore wind, hydrogen, tidal, and floating PVs. Some of the speakers will also discuss the potential utilization and deployment of these technologies across the wider MENA region. Now, the list of, I will just put the first slide here. It's the cover slide, which has all the list of speakers and the sessions here. So we have got a very varied and very good list of speakers across the renewables and new energies market that we will discuss today. And without further ado, I would like to call our first speaker, Professor Lourdes Vega from Khalifa University, and request her to take the podium for presenting session 1, Revolutionizing Energy Systems. How do we meet evolving customer needs through renewable hydrogen, CCUS, and electrification? I would like to do an introduction of Professor Lourdes Vega. She is the director and founder of the Research and Innovation Center on CO2 and Hydrogen, which is the RICH Center for Khalifa University, and the acting senior director of the Petroleum Institute at Khalifa University, with responsibility for research, development, and innovation on CO2 capture, utilization, and storage, CCUS. The whole value chain of hydrogen and sustainable fuels, in addition to her teaching duties as a professor of chemical engineering. Prior to joining Khalifa University, Professor Vega worked in different geographical areas and institutions, both from academia and industry in the USA and Europe. Since she has been involved in fundamental and industrial projects related to CO2, hydrogen, and clean energy for more than 25 years now. Her contributions in clean energy and sustainable products have been recognized with numerous awards. Among other recognitions, Professor Vega received in 2020 the Mohammed bin Rashid Medal of Scientific Distinguishment and the Award in Physics, Innovation and Technology by the BBVA Foundation and Spanish Royal Society of Physics in 2013. Over to you, Professor.
Thank you very much. Yeah, I will need. Thanks for the presentation. Thanks for being here. On the title of the event, I am on the second part. on the new energies. I don't know much about the offshore, but we will have other experts for that. In fact, I'm going to give an overall presentation on what do we need to revolutionize the energy system. I don't think this is my very last version, but that's okay. Thank you, thank you. Okay, so first I'm going to give you a few words about the Research and Innovation Center on CO2 and hydrogen. This is a center that was launched in Khalifa University in 19 year, where we covered, as it was said, the whole value of chain for CO2, hydrogen, and sustainable fuels. This is one of the largest centers in the university. We have more than 80 researchers, 21 faculty, postdocs, research engineers, graduate students, etc. Some of them are here today, some of them will be later. The way we divide our work is in 5 different thematic areas. We work on materials and processes, both in CO2 capture and separation and sequestration, CO2 utilization, hydrogen production and storage, hydrogen distribution and utilization. And all of them are linked among them, as you can see, because we produce hydrogen to be utilized, but we produce CO2 and hydrogen for synthetic fuels, for example, or we produce blue hydrogen when we capture the CO2. So all the topics are interrelated, making the center much stronger. And one of the main applications is as well sustainable fuels. Of course, as part of a university, we work heavily on education, training, and dissemination of our work. We work together with universities, government, and companies to achieve this. Actually, some of the students will be here today in some of the sessions. So this is the REACH Center. We have one theme lead for each topic. Some of them are here today. And then we have different faculties who are experts in the different aspects. For example, CO2 storage, we have some of the experts here today, hydrogen utilization, etc. And in the center, we have labs that belong to the center that actually are in the building next to us over there. For next time, we can invite you to come. And then we also use the core labs of the university. We have, let's see if I do it properly. So we have some of the pictures of the labs that we have here, and these are some of our stakeholders and international collaborators. This is not my last presentation. Is this the one I sent you? Okay, that's weird. Okay, I will do because I don't know what is coming. This is not the one I prepared yesterday. So let's see what we get. So what is the situation today regarding, let's see if I have it later. No, really, it's not the last one. Anyway, doesn't matter. I managed with it. Okay, so when we talk about revolutionizing the energy system, we talk about COP, we talk about all these things. In the end, what we are talking about is what do we do to mitigate climate change? When we talk about mitigating climate change, one of the main issues is the bad boy of the movie, which is CO2. CO2 is not bad, it's just that we have an excess of CO2 into the atmosphere that we need to handle. So how is the situation today regarding CO2? So this is and a slide that I will present in all my talks, in which you see in the period of 5 years, what is the CO2 concentration of CO2 in the atmosphere in the period of 5 years, as I say. So the red line is the monthly mean value centered in the middle of each month. And the black line is the average per season. And this is always measured in the manual. This is the situation right now. So you see the plot is very similar. However, the numbers are not the same. So this data is from September 5th. They update this data and they all up every month on the 5th of the month. So this is the last data. So what we see here is that if we look at the numbers, compared to last year at the same period, we have more than 2 ppms with respect to last year. But 2 ppms is nothing, parts per million, correct? The problem is that every year we have 2 more ppms since we started to count. That make a difference. And in fact, when you look at the numbers, in 2007, we had less than 385. In 2023, we have more than 422. Again, this is small. Okay, let me give you some data from experts. The experts in environment say that when we reach 200 and 410, we will have irreversible things into our planet and the atmosphere. So we reached that in 2019. And we thought, oh, maybe that appeared in the media everywhere. But then people were thinking, oh, this is a point in the middle of nothing. Let's see what happened next. You can see what happened next, correct? I don't have to explain. The data speaks by itself. Doctora, this is only for 5 years. Okay, this is what happened in the last 63 years. So the trend is clear, correct? Okay, where are these emissions coming from? So this data comes from the latest report that we have, in which it shows that the CO2 emissions reach the highest ever number last year. By the way, the numbers from 2022 just arrived and they are even worse than that. And where are these emissions coming from? They are coming essentially from the energy power, also for transportation, and from industry. You see, this is not my last slide. Anyway, that's fine. So in the end, what we are going to talk today and for the rest of the meeting is we are in a planet in search for sustainable, secure, and affordable energy. This is the trilemma. We need to have this. So where are we today? This is the total emissions that we have in 2020, the one where we have the green line. And this is where we need to be. All these numbers, colors here are the different scenarios depending on what we do. And what we see is that we really need to come down to this for the 1.5 pathway or to this for 2, which means we need to do many things if we want to do it by now. Maybe especially for the young people, you think that 2050 is too far away? It's not that far away. We will see that to arrive this to 2050, there are things we need to do today. And essentially because we didn't do the things we had to do yesterday as well. So this is really very, very important. So what can we do? I don't need to invent everything. Einstein already said, those who have the privilege to know have the duty to act. And this is our case. We all have this privilege. We don't need to invent any new thing. The International Energy Agency published a beautiful report that I'm giving you here, the link, on the energy systems overview that give us different possibilities for tracking how we are doing. That's what I say, correct? Where are we today? Where do we need to be? Where have we been? Okay, so now I put these lines. At least this is new from the one last week, but this is not my last version. Anyway, so what I'm going to show you here is in all these little different things that I show here, how are we doing with data, okay? So you don't have to go into the details of the data. What you have to do is look at the trends and see if we are arriving to where we have to arrive. And because I said 250 is far away, let's look at 230. 230 is 7 years from now, almost 6 years from now. So let's see how we are doing. So the first thing is, so these are the contributions to the clean energy revolution. So the first thing we need to do is energy efficiency. This is how we have been doing. The line shows where is the trend, and this is where we have to be in 2030 to reach what we have to reach by 2050. I like the second one because the second one is in the hands of everyone, which is the behavioral changes. And here we have 3: cars, aviation, and heating and cooling. So in blue, you have the activities, and in green, you have what is avoided due to the behavioral changes. And one means the activities in 2021. So we can see that actually is growing, and the contribution from the behavior is very small, to tell the truth. Others, so we have here industry, residential, and road transportation. You have the lines, and you see that we are not hitting them. We are doing okay, it looks, but we are not hitting that. Electrification and renewables, 2 of the topics we have today. In electrification, we are growing of course, in buildings, also in industry, a little bit more on transportation. On renewables, my God, this is the trend we have in renewables. We think we are investing in renewables. We need to invest much, much more. For this, we need to have more efficiency and also lower cost, of course, and energy management, as we will talk later. How are we doing in hydrogen and CO2 capture, the ones that we work at REACH? Okay, not very good, as you can see. In the CO2 capture, actually, there are 2 trends. This is where we were until this year. This is the new trend, which is really growing, but we need to do much more to achieve net zero. And then we have other systems like clean energy innovation. Digitalization is helping us a lot. But if I put lights to this, no one is green today. Some of them are yellow, some of them are red. The ones in red are the ones we need to work more. Okay, and that goes to the report by Irina that give us 6 technological avenues for the energy transition that will allow us to reduce the emissions by 2050. So these are renewables energies, 25%. 25% will come for efficiency, 20 by electrification, 10 by hydrogen, and the rest remaining 20 by CCUS from biomass or from fossil fuels. So you see the topics we are addressing today in the workshop are all relevant to these 6 avenues that we need. So it's clear that we need to work on low cost power, efficiency, electrification, bioenergy, hydrogen, etc. And this means that we need to take radical actions, as I show you, and also requires political will to help. We have COP28 around the corner. We hope they come with commitments that we follow this path, and also technological changes. So the new people here, young generations, there is room for all of us to work on this. Okay, so if we talk about CCUS, this is distracting because I had another talk, but anyway, when we talk about CCUS, we are talking not only about the capture, in which we see here the different technologies that can help us to reduce the cost of CO2 capture and the time to commercialization. So these are the ones that we can do it right now, but the cost reduction is very small. These are the ones that we can work on, and the cost reduction is a little bit bigger. But in addition to CO2 capture, we also need to purify it, transport it, and store it, which is one of the talks we will also talk about it today. Okay, but why don't we utilize it? It's much nicer. I wrote a book about this in 2010, and it's really much more attractive, but we have to be realistic. What are the numbers? I say that the total CO2 emitted was 36.3 gigatons in 2021, and the applications, including enhanced oil recovery, was 230 megatons. So this is 0.6% of the total. So even if we work, on it, we still have a long way to go, and we will need to store the CO2. And of course, we also need to work on renewables, energy efficiency, etc., to cover all the different things. So where can hydrogen help? Hydrogen is not a primary source of energy like wind, that we will talk about this later, or sun. So hydrogen, we need to produce it. It's called an energy vector. But the beauty of hydrogen is that it allows to store energy. So it's a very nice combination when you have this with renewable energies. And in fact, this is the paradigm of hydrogen today. I have been working on hydrogen for 25 years. The hydrogen that we were working for was for transportation, for refineries, for fertilizers, how to improve the efficiency of the processes, etc. Now, hydrogen can be used for other things as well in the context of clean energy. And this is the revolution. So where can hydrogen help? Hydrogen can be used if we have an excess of renewable energy. Then we break the water molecule, we produce hydrogen and oxygen, and then we will use this hydrogen when there is a defect or we don't have enough renewable energy, for example. And once we have the hydrogen, it can be used for many applications that we will see later: transportation, steel making, cement, etc. How is hydrogen produced today? My students can answer this. Today, most of the hydrogen is produced by steam methane reforming. That means methane, fossil fuel, water, and then we produce hydrogen and we emit CO2 into the atmosphere. That's called gray hydrogen. 1 ton of hydrogen produces 10 tons of CO2. So that means it's a huge impact. And that's why we talk about blue hydrogen. But anyway, we are now working very hard on moving other technologies that have lower hydrogen footprint. This is the whole value chain of hydrogen. I hear you have heard about the different colors of hydrogen. Hydrogen has no colors. It's a gas, no colors. When we talk about the colors of hydrogen, we talk about the molecules from where hydrogen is produced and the source of energy we use to produce this hydrogen. So for example, gray is the one I explained. So we have methane and water, we produce hydrogen, but we emit CO2. If we capture the CO2, that becomes blue hydrogen. If instead of using methane, we use water and renewable energies, and the and is capital, we need to use water and renewable energy, then we have green hydrogen. The strategy of the UAE is blue and green hydrogen, and it's not only of the UAE. And then we have other colors. Once you produce the hydrogen, you need to transport the hydrogen. That's another huge issue, We need to first store, and we will talk about this later also in the workshop, but we first need to transport it. So we can transport it, for example, blend it with natural gas. We can transport it as a pure hydrogen. That's very difficult. Hydrogen is a very light molecule, so it requires a lot of energy and low temperature to transport it as a compressed liquid. And then we can also use hydrogen carriers or different options. We can convert the hydrogen into ammonia, then we transport ammonia, and then we can crack ammonia again to recover our hydrogen. And then, of course, once we have the hydrogen, we can utilize the hydrogen for the classical applications we had before, refinery, fertilizers and chemical for producing methanol, but also for other applications, energy storage, as I say, combined heat and power, and heavy transportation. Not all these technologies are mature. Not all of them are low carbon. For example, gray is not low carbon, and not all of them are used at large scale. That's why we need to move what we call the hydrogen economy. So what is blue hydrogen? I already mentioned what is blue hydrogen. So this is for the engineers, a mass and energy balance on how to produce blue hydrogen. So we have here the amount of heat, water, and methane we need. Then we have the reaction, and then we get the hydrogen. This all is based on 1 ton of hydrogen, and then this is the CO2 we recover. We don't put 100% because we are scaling over 1 ton of hydrogen. We can do the calculations in a different way. What about green hydrogen? So green hydrogen, as I say, is produced by electrolysis. It could be produced by other ways, and it requires double amount of water than blue hydrogen and 5 to 7 times the amount of energy. So this is the problem. We require a lot of energy to produce hydrogen. So that means we need to have low cost for renewables. We are in the right place. We are in the right place for everything. So we have oil and gas, we have sun, we have low cost of solar, etc. So this is very good. But again, solar is intermittent. So we need to see how we combine that. We need fresh water. That could be an issue for the UAE. We don't have water, and we use the water for other needs. But still, we can work on going around all these applications, all these issues, and have very, very good opportunities for green hydrogens. That's why we have green and blue hydrogen. So these are the main ways of producing hydrogen. And this is the forecast for hydrogen production if we move on the hydrogen economy. The colors are the colors that I say before. So gray, blue, and green. You can see now today we have only green. We are moving a little bit into blue and green. In 2 years from now, by 2030, still more blue than green. And then as we move on, we go with green, blue, and we still have gray. Where is hydrogen used today? So today, hydrogen is used, as I mentioned, in the different areas. In total, we produce only 87 megatons of hydrogen. I don't know if you remember what we use of CO2. Do you remember? 230 megatons of CO2. So CO2 is much more utilized today than hydrogen. And it's because of the applications we have. But we expect to get this with the new applications, especially heavy transportation, synthetic fuels. So that's to decarbonize the hard-to-abate sector of heavy transportation, including aviation and maritime sector, ammonia, the metal production, and heat and power. So this brings us to 2 main areas that we talk about, which is regarding CO2, we have to work on different aspects. So I put here, this is from McKinsey. I say this is for our customers. So we need to see where the business opportunities are and where do we have to work in these sectors. So for CCUS, this light gray is storage. That's why in the UAE, we are working heavily on finding the best way to store the CO2 that we need to capture. And this big one, black, is for producing synthetic fuels, because that's what we will need if we don't use fossil fuels. Then we have carbonation and some other treatments. For hydrogen, I already mentioned it. This is really funny. So anyway, the final remarks, these are new times, new challenges, and new business opportunities for all of us. This is a challenge, but it's really an opportunity. It's an opportunity for developing new technologies. It's an opportunity for getting old technologies and putting them in a different application, working with the final users, working with the universities. So we need for sure a different combinations. We need to have renewables with energy storage. We need to have electrification. We need to have energy efficiency alternative sources of energy. I didn't talk about from waste to energy. This is very important. Bioenergy includes waste, is one of the main areas in which we are moving for producing electricity and power. Research and innovation is clearly needed. We need to find more efficient processes, environmentally friendly and affordable. We need to combine fundamental science with technology development and implementation. Let me give you some numbers. The breakthroughs will come from fundamental science. And that's why we need to collaborate, all of us together. So the joint efforts with administrations, the government of the companies, and as I said, we need to work together, but believe me, we need to invest. There is no free ride. What we invest today will show up in the future. And the future is here. I'm taking this from The Mysterious Island, Jules Verne. Only about hydrogen. Actually, as I said, this is not my last talk, my last slide, but it's okay. Water will be one day employed as a fuel. Then hydrogen and oxygen, which constitute used singly or together, will furnish an inextinguishable source of heat and light intensity, of which coal is not capable. And this is 1874. You know why we didn't move with this? Because we discovered oil and we discovered engines to best use oil. This is very interesting. But now we are coming back to this, correct? So with this, I finish my presentation and I will be open for questions today or now or later. I think later. Later?
Thank you, Professor. Thank you. We'll do question and answers later on, okay, combined. That will save us a bit of time. Okay. Thank you so much. You're welcome. So I'll keep this for some time before we call in the next speaker. Thank you, Professor, for setting up the scene. It was fantastic. I think I can say, at least for our bit of presentation, which is session 6, that you have kind of made the start of the presentation a bit easy while we focus on the other subject of the presentation. I'm sure it will be true for the other speakers as well. So now I would like to call upon Riley Smith from Xodus Group, session 2. Riley Smith is head of Xodus Group's advisory practice across the Middle East and Africa. Riley holds a BSc Environmental Science from the University of Adelaide and has 13 plus years of experience in consulting in the upstream and renewables energy sector. He has been based in the MENA region for last 8 years and has been responsible for architecting and delivering a number of CCUS studies to clients in this region. Over to you, Riley.
Firstly, my bio is not nearly as decorated as Professor Vega. That's a great start to the day. And obviously there's a lot of hot topics made even more important with the COP28 event coming up in the UAE later this year. A quick disclaimer before I kick off. I was hoping to have our global CCS expert, James McCreevy, with us today delivering this presentation, but he was unable to join. So I'm by no means an expert, but Xodus, the company I work for, I think can be considered as an expert in the CCUS space. And what I'll try and do is give you a little bit of background into the CCUS sector and try and give you a bit of an overview about some of the challenges we've seen as a consultant in the various projects that we've been involved in. I'd also like to thank SUT for the invitation. I believe this is the first time that we've been involved with the society, so we appreciate it and we're very happy to be here. And also a quick thank you to Khalifa University for hosting us today. And yeah, looking forward to the rest of the day's topics as well. So just a very brief introduction on Xodus for those of you that might not be familiar with us. As I mentioned, we are an international energy consultant. We were established 18 years ago. We had our 18th birthday at Offshore Europe in Aberdeen just last week. So we're UK focused, or UK headquartered, sorry, or Scottish to be precise. and we've been in the UAE for over 12 years. We provide a range of technical and commercial support to clients across the energy spectrum, and our capability includes energy advisory, subsurface and surface engineering, which I'll touch on a little bit later, and how important that is for the CCUS space. And we've also got a very large environmental and renewables capability, as well as supporting the development of supply chains in these new energy sectors that we're talking about today. So why are we qualified to talk about CCUS? So I'll just give you a little bit of context on that side. Firstly, we've been doing it for many years. We've been doing it for over a decade. We did our first CCUS project in 2011. And I guess there's a couple of points to note here, which are quite important in terms of delivering CCUS projects or CCS projects. Xodus is one of the limited number of companies globally that have experience in actually operating industrial scale CCUS storage systems. And what this has allowed us to do is bring those lessons learned from the early days into the early phase design of the projects that we're now looking at, which is super important in terms of being able to make these projects more successful and, more importantly, economic. We've got that integrated subsurface and surface, and I'll touch on that later. As you'll see, one of the biggest challenges we have in the CCUS space is around the uncertainty and the monitoring around what happens to that CO2 when we inject it into a store. So what is CO2? Firstly, it's nothing new. It's a gas that we've been dealing with in the upstream industry since day one, so we've got a pretty good understanding of it. It's corrosive when saturated with water, which is a bit of an issue when you look at an underwater scenario. But as we'll find out, there are solutions. It's pretty clear that CO2 is bad for the atmosphere. I think that's a well-known fact. And I guess due to human nature and the things that we want and need in terms of energy, infrastructure, we're going to be producing CO2 for the foreseeable future. So we really need to find a way to sustainably continue to develop, but dispose of this nasty gas appropriately and economically. So for those of you who aren't familiar with CCUS, I'm just going to give you a very, very brief overview. It's pretty self-explanatory. It's taking CO2 from the atmosphere and putting it somewhere else where it doesn't escape. Another name that we could have given it is hazardous waste disposal, but that doesn't have such a good ring to it when you're trying to get investment. The capturing obviously refers to collecting the CO2 at atmosphere or from the atmosphere or directly from an emission source. And utilizing simply means using that captured CO2 to create more valuable products, such as fertilizers and other useful chemicals. And storage does what it says on the tin. It's putting it somewhere where it hopefully stays for good. Now, I wanted to just give you a bit of context as to why CCS is important. And I think Professor Vega touched on a lot of these numbers, and I hope that these sort of match up fairly closely to hers. But for starters, CCUS, CCS is widely considered to have quite a large impact in terms of arresting the current emissions position. So it's quite important for the climate change situation that we're in. In the IEA Sustainable Development Scenario in 2019, it was estimated that 2.3 gigatons of CO2 would need to be stored by 2050. Now, with many governments and organizations now committing to net zero by 2050, that magical number that we keep seeing, that number now increases to 4 gigatons per year. To put this into perspective, the current global installed capacity is around 0.04 gigatons. So we need to increase the current capacity in the order of about 100 times in order to meet those climate change goals by 2050. So it just shows you a little bit of impetus in terms of this is not an onshore and offshore scenario, it's an everything scenario. And as I'll get into it, the challenges that we see in the CCUS space are common across both onshore and offshore scenarios. And we'll get into that in a little bit. But how does this play into the MENA region? Well, it's not pretty. So we have some of the world's highest emitting nations per capita in the region, and with about 85% of those emissions coming from the production of oil and gas or the related industries. So we see this as a real opportunity for the MENA region in terms of we've got an excellent oil and gas heritage. We've got a lot of skills and understanding from a subsurface perspective and also surface infrastructure. So there's a real opportunity to deploy that knowledge and expertise to accelerate the CCUS market globally. And I really feel that the Middle East can become a leader in the CCUS space. And I guess CCUS should be considered as a vector as well to driving sustainable economies in the region. Oil and gas is going to be around for a long time, but perhaps its use might become less valuable. So to sustain these economies, we need to start thinking about ways in which we can decarbonize those revenue streams to allow the countries that we all live in, some of us are visiting, to flourish in what we would then see as a very low carbon environment moving forward. So obviously there are a lot of challenges when it comes to carbon capture, utilization and storage projects. And as I said, a lot of these challenges that we see as a company and the projects that we work with are quite common across both onshore and offshore environments. But I'm going to touch on a few of the major issues that we've come across and try and give you a little bit more color as to how, or just frame how we might be able to deal with these moving forward, especially with events like COP28 coming up in the UAE later in the year. So the first point I'd like to make is that there are a lot of commercial complexities when it comes to CCUS. There's not a lot of intrinsic value in CO2 currently, meaning that there isn't a lot of profit available under the current conditions to warrant that large upfront capital spend to develop these types of projects. And I guess it's very similar to what we've seen in the offshore wind market in the UK this week, where they're not able to get that forward-looking confidence in pricing moving forward, which is scaring the investors off to actually make those development decisions. CCUS is complex, you know, it's a difficult task. It's hard to do, so generally that means it's quite expensive, and it can actually be quite energy intensive to set up. So that's something that you've got to bear in mind when thinking about these CCS projects. I guess the elephant in the room is there's always a stigma associated with CCUS around its apparent contribution to prolonging industries like the fossil fuel industry. And that is, you know, a challenge that we see every day, and that's without throwing, you know, the other aspects of that energy trilemma into the equation. So it's a complex subject on its own, but when you throw in the other elements into that energy trilemma, it becomes even more complex, and the economics become even more difficult. And I guess the biggest problem we have from a technical perspective is ensuring that the CO2 stays where we put it. You know, we know a lot about the properties of CO2, but there's still a lot of uncertainties and risks that we see in the subsurface environment. And that's apparent in the oil and gas sector. You know, that's just something we deal with. It's trying to mitigate those risks that is the tricky part. So just some of the technical challenges, and I'll touch on these in a bit more detail in a little bit of time. But you know, generally capturing CO2 from low pressure. So although CO2 capture is well established, it's generally moderate to high pressure. So the lower the pressure, the bigger the equipment you need, the more energy intensive it is. And all of a sudden, the economics then become a little bit shaky. I touched on it earlier, but CO2 is corrosive, especially when saturated with water. So when you're thinking about the materials that are required for a CCS project, you need to put a lot of thought into making sure that your pipelines and infrastructure are designed with enough robustness to cater for that store's life. And that's where we get into the tricky nature of using existing facilities and infrastructure that haven't been designed with the thought of potentially using them for CCUS. So it's very difficult. It's very difficult to deal with. The other one is custody transfer. So as it's been considered a hazardous waste product, it's very important that we know where every molecule goes in terms of getting approvals from the regulatory framework in where we're operating. So that is one of the biggest challenges that we see, and that also needs very robust planning. So I'll go into a little bit more detail on a couple of the challenges that we've already sort of mentioned. Transportation is obviously one of the challenges, but it's not the biggest challenge for CCUS. It is a challenge, but I mean, hydrogen has far bigger challenges in terms of transportation. But generally speaking, stores are located quite far away from the emission source, meaning long distance pipelines, infrastructure, and that all adds up to the costs. And when you link it back to that intrinsic value of CO2, it becomes quite tricky. One of the other very important factors in the challenges we see in CCUS are around the leak monitoring and detection. So it's around that piece around ensuring that the CO2 stays where we put it. That needs to careful consideration, and that program needs to be designed with a lot of robustness. And I'll touch on that again in a little bit more detail later on. Shipping is obviously more complex. We want to transport as a liquid, the CO2 as a liquid, either at high pressure or semi-refrigerated. But currently in the world, to my knowledge, there are no ships that can cater for that, and that's without adding some of those tricky design challenges around storage tanks and the ship stability. So it's a tricky topic. In terms of the stores and the injectivity, I mean, the stores remain the same, whether it's onshore or offshore. We've generally got two types of store in the CO2 storage space, and that is saline aquifers, which are generally have a lot of storage capacity, but the main challenge is the lack of understanding of their geology. And that makes it tricky to prove that the CO2 will stay where we put it. The other option is depleted oil and gas reservoirs. Generally, these have got a lot of storage capacity when the reservoir is still under pressure, but still depleted with pressure, sorry. And we understand the subsurface elements of these reservoirs in much more detail because we've been producing oil and gas out of them for some time now. However, with existing reservoirs, we have the problem of existing wells and infrastructure presenting, potential leak paths, and that makes the whole operation all the more tricky, especially when you have a field that you've got previous operations that haven't taken into consideration in using CO2 resistant cement, for instance, or the poor plugging and abandonment of previous wells. From an injection point of view, saline aquifers are relatively easy to inject in, as the reservoir pressure has to stay relatively positive. The main issue in the saline aquifers is the issue of faulting, causing segregation in the store and rapid pressure, which leads to you having to bleed the brine out to maintain pressure. In the hydrocarbon reservoirs, the issue is more around the the upstream transport. If the pressure is high in that upstream transport system, then the pressure in the reservoir will naturally rise over time, and that results in the injection conditions changing over time as well, which means you need to think about that. So cold temperatures due to choking, various tube sizes or well counts, it's all tricky to maintain that constant injection pressure or rates over the life of the store. So this is perhaps the biggest challenge around CCUS in the current climate, and it's around that question about how do we make sure that it stays in the store and doesn't leak back into the atmosphere. And to be honest, I think this is a question that we will get a more accurate answer for as we move forward together and we collaborate and we gain more experience of dealing with these types of projects. But for now, these projects require a lot of subsurface monitoring, which is generally expensive. And again, it comes back to linking it to that potential value of CO2 being injected. And the economics of a project can look very shaky very soon. But again, I think, with COP28 coming up in the UAE this year, I think this should be on the agenda. And I would hope that the nations visiting COP will start to have that discussion in a bit more detail around creating a little bit of uniformity around global carbon pricing, because that will really accelerate the rollout of CCUS projects across the globe. And that's really what we need. And as industry, we could only do so much, but we need to sort of lobby the governments to be able to get to that space where we can start to roll out these projects. We need to accelerate the deployment of CCUS. Our industry has the capability to do that, but it comes back to those commercial dynamics. And that's what comes to my last slide, which is a different slant on the challenge. It's not a technical challenge, but it's the commercial dynamics of offshore versus onshore, which I wanted to touch on just to give you something to think about moving forward and something to take away. But I guess one of the commonly perceived barriers to CCUS is cost. However, our observations point towards the choice of a location, whether it's onshore or offshore, are actually driven by public perception and not always costs. For instance, in Europe, 100% of the advanced stage CCUS projects are offshore in the North Sea, and that is driven by public perception, land availability, dense population. So they have to choose arguably the more expensive, slightly more expensive place to be delivering these projects. I thought this might be an interesting way to finish, just to start thinking about, because it's the opposite of what we've got here in MENA, where we've got a lot of space. We've got the abundance of clean energy from the solar, and we've got a lot of oil and gas that creates that CCUS. So I feel that there's a huge opportunity for us to come together to really be the global leaders, not in oil and gas now, but for the future in CCUS. So yeah, thanks everyone, and I look forward to the rest of the talks.
Thank you, Riley, for giving us an overview of CCUS, the challenges that are out there when we talk about CCUS from the offshore perspective, and also at the end touching upon the commercial dynamics. Thank you. I invite our next speaker, Yasser Khoker from Worley. His presentation will again touch upon the interesting topic of offshore wind. Yasser is a civil engineer by training with more than 18 years experience of working in consulting and contracting organizations in the UK and the Middle East. Yasser completed his undergraduate engineering studies at University College of London, postgraduate engineering research-based master's degree from Cambridge University, and MBA from Imperial College London. Yasser is a chartered engineer with the Engineering Council of UK and a fellow of Institution of Civil Engineers UK. He is a consultant within the advisory consulting arm of Worley and leads studies exploring the early stage techno-economic feasibility of projects across various sectors, including oil and gas, ports, mining, and renewables energy sectors. Ladies and gentlemen, Yasser.
Good morning, everybody. Thank you, Ashish, for that introduction. Thank you to Society of Underwater Technology and Khalifa University for hosting us today. So thank you to Professor Vega and Riley for setting the context for this talk today, and really the challenges that we face in terms of meeting our targets in terms of net zero. And really, we believe that we're going to require a toolkit, a portfolio of toolkits. And, one of the things that is overlooked in this region is the offshore wind. And I'll just give a brief overview of the offshore wind potential in the Arabian Gulf region. So just an agenda for the presentation, just quickly talk about a little bit about Worley, the company, if some of you are not aware of what we do. Then give an overview of the offshore wind across the world, and then we'll focus in specifically on the potential of offshore wind in Arabian Gulf region. And I'll just finish off by giving a brief scenario example. So just a quick introduction to who we are. Worley is a leading engineering consultant. We do early stage feasibility studies right to through front-end engineering design all the way through to doing EPCM type models, engineering, procurement, construction, management type models. We're the #1 in hydrocarbon services, in chemical services, and we're also doing a lot of work in renewable energy with over 1,500 projects completed to date. We're driven by a common purpose. Our purpose is delivering a more sustainable world, more sustainable solutions, more sustainable communities, and a more sustainable environment. Something else that we're really proud of, we have over 50,000 people across 49 countries, spread across 250 locations. So there's always a person with the right skills and experience to speak to. So just an overview of the offshore wind. This is a quote from the International Energy Agency Director, Mr. Fatih Birol. And he says that offshore wind's potential is near limitless. Improved technology and steep cost reductions are putting more and more of that potential within our reach. So we believe that the need for affordable low carbon technology is greater than ever, and the offshore wind is definitely one of the tools. It's been identified as one of the big 3 in the energy scenarios, projected alongside onshore wind and solar PV to be one of the main sources of electricity in the global energy transition. Like onshore wind and solar, it's a form of renewable energy that's clean, cheap, and reliable. And this is just a short video introducing offshore wind and our vision of our role in driving this change.
The direction of offshore wind is changing. It's not just about powering the grid, it's about decarbonizing the world. Everyone has an ethical decision to make about the source of their energy, and the biggest changes can only come from within. Companies that work in carbon-intensive industries have a responsibility to lead the way in building a net zero future. And the race is on to get more offshore wind farms up and running safely. As wind markets emerge in new geographies, the industry depends on a workforce who are on the ground and ready to go. Experts who understand the problems and can build cost-competitive business cases to get the fixed and floating turbines energized on time. But it all means nothing if the turbines don't spin. It's about applying the right digital tools and finding smarter ways to operate and maintain assets. But using offshore wind to produce electrons is only the beginning. Piecing together all the parts of the renewable energy puzzle to integrate into your operations is complex. After many decades of safely delivering the world's largest projects, for us, it's business as usual. The time is now.
So, as I said, we believe that offshore wind across the globe is one of the toolkits as part of the energy transition. The ocean winds are an inexhaustible source of renewable energy. According to the IEA, offshore wind energy could power every home and business on Earth. However, most of this potential of wind power is currently going to waste. The only way to capture it is with tens of thousands more offshore wind turbines spinning on coastlines across every continent. The world's net zero ambitions depend on making this a reality. Produced by wind turbines installed typically in shallow waters of less than 50 meters deep, offshore wind farms are usually located in nearshore locations. Currently also there's floating wind, which is challenging the evolution of wind farms by allowing turbines to be installed much further, benefiting from even more reliable and consistent energy. Coastal winds, just a brief background on how energy is generated. Coastal winds help to turn wind turbine plates, spinning a shaft connected to a generator. This generator turns the kinetic energy into electricity, which is sent to substations and fed into the electricity grid or distributed to industrial users. So just this slide provides an overview of some of the key advantages associated with offshore wind. Offshore wind speeds tend to be faster than on land. Small increases in wind speed yield large increases in energy production. A turbine in 15-mile-per-hour wind can generate twice as much energy as a turbine in a 12-mile-per-hour wind. Faster wind speeds offshore mean much more energy can be generated. Also, offshore wind speeds are more consistent and steadier than on land. A steadier supply of wind means a more reliable source of energy. These factors increase energy output because the turbines are consistently spinning for longer. This usually leads to higher power generation from offshore wind farms. Another advantage of offshore wind farms is obviously that they're less disruptive to most landscapes, as these wind turbines are often located beyond the horizon. Most coastal areas have very high energy needs. Almost one third of the world's population is located within 100 kilometers of the coastline. For example, half of the U.S. population lives in coastal areas with concentration in major coastal cities. Building offshore wind farms in these areas can help to meet these energy needs from nearby sources. Offshore, as I already said, offshore wind sites can supply more than the total amount of electricity. And if we were to move even further offshore into deeper waters, it could meet the world's energy demands 11 times over, according to the IEA. Offshore wind farms have many other advantages. They provide renewable energy, do not consume water. They provide a domestic energy source. They create jobs. They do not emit pollutants or greenhouse gases. I should say here, just to end, I mean, there's a host of disadvantages obviously associated, and we will see some of them when we specifically talk about the Arabian Gulf region. It's an energy source that is, it's the increasing costs in the current inflationary market. We had the UK auction last week for offshore wind, and no bids were attracted because of this inflationary market. There's a lot of upfront investment requirements, met-ocean condition concerns, supply chain limitations, and the grid build-out requirements. So this slide just provides an overview of the increasing momentum in the offshore wind market. It's a rapidly maturing renewable energy technology that is poised to play an important role in future energy systems. Turbines are growing in size and in terms of the power capacity that can be generated, which in turn delivers major performance and cost improvements for offshore wind farms. Government and established markets are raising installation targets and holding auctions. As I said just now about UK, for example, while several others are busy setting first goals and passing enabling legislations. As governments worldwide set net zero targets, targeting even wind build several multiples higher than today, the wind industry has proved it can deliver sustained growth. In 2021, global commissioning of wind turbines reached almost 100 gigawatt for a second year running. And offshore wind additions surged almost 161% year on year. Just a chart over here shows Bloomberg's 2021 offshore wind market outlook, which foresees the sector to expand almost 11-fold to reach 400 gigawatts by 2035. So now I'll focus more in on the offshore wind potential within the Arabian Gulf market. These charts show the potential of offshore wind in the Arabian Gulf region. According to some estimates, the Arabian Gulf and the Gulf of Oman's shallow areas have an estimated 1,000 gigawatts of offshore wind energy potential, which could considerably help the region meet its renewable energy goal. The potential of offshore wind has been investigated and studied by several countries already. For instance, the UAE is conducting feasibility studies, and I believe that Saudi Arabia has already got plans to construct their first offshore wind farm. So the chart here on the left shows the average wind speeds in the region, and the chart on the right shows approximately wind power density. So the darker areas show higher wind speeds and higher power density in these charts. These charts are from Kuwait Institute of Scientific Research. We can see here that in specific, the offshore fields just to the east of Saudi eastern seaboard and north of Qatar have the most potential for further studies and evaluation. In terms of constructability, and here's really the the advantages that Middle East particularly has. The cost of construction of offshore wind farms is significantly driven by the seabed depths, which in Arabian Gulf region, as can be seen from the chart over here on the top right, immediately east of Saudi, eastern seaboard, and the north of Qatar, the nearshore water depths are typically in the range of 0 to 20 meters. And when you come closer near shore, they range from 0 to 10 meters. In addition to that, based on the offshore work already taken for various oil and gas related projects in this region, we have a fairly good understanding of the generally favorable ground conditions, and therefore have a suite of suitable cost-efficient foundation system solutions, which is a key driver for the overall cost for offshore wind farms. Furthermore, over here in the bottom right, we can see typical wave rows for the eastern, just off the eastern coast of Saudi. The wave conditions are relatively benign when compared to some other regions, for example, like North Atlantic region, further simplifying the design and construction of offshore wind farms in this region. In addition, there are significantly other advantages from a constructability perspective. These sites are located close to fairly dense, high energy consumption areas, such as offshore oil and gas fields with significant energy demand. Also, the sites are generally located in areas under the development control of major oil and gas groups, which are the de facto custodians of the maritime area, the nearshore maritime area. Lastly, with the amount of development that's already going on over the past few decades in association with the oil and gas facilities, there's a readily available source of local workforce with the key skills and experience, local contractors and equipment to undertake this work in fairly well-established and well-understood conditions. So this slide presents the potential output capacity of a wind turbine in this region. Wind turbines produce energy when wind speeds are between 13 and 13 kilometers per hour and 75 kilometers per hour. From the top right chart, and considering the blue line, which is the wind speed, we can see that wind speeds are below 13 kilometers per hour, around 40% of the time for a typical high potential site in the region. That is one of the reasons why it's not used regularly as a reliable power generation. Now, if we consider the green line, the power output for a 6 megawatt turbine, the maximum power of 6 megawatt is only generated when wind speeds reach 50 kilometers per hour. But here's the point of the presentation. If we try to make an economic case, it's a little bit more shaky. But if we change the objective of the exercise, offshore wind in Arabian Gulf provides reasonable opportunities to meet net zero targets and diversifying the energy supply. In other closed areas, geographical areas such as Oman, south of Oman, or East Africa region, reliable power generation from offshore wind is being used alongside rapidly developing electrolyzer technology for hydrogen production, as touched upon by some other speakers. However, it is key to remember here that while power generation is less reliable, the cost of construction is also much less in the Middle East region due to what we discussed earlier. For example, shallow seabed, good ground conditions, good availability of local contractors and consultants when compared to some other locations. So I'll just give a brief example scenario of where this offshore wind could be potentially be employed and in what situation. So this slide just presents a potential example of 50 wind turbines located offshore Saudi eastern seaboard, close to an operating oil and gas field that is a fairly high energy consumer. It has been assumed that 50 wind turbines would have a maximum power rating of 6 megawatt with a yearly output of 15,000 megawatt per single turbine and 770,000 megawatt hours for 50 wind turbines. The wind farm is located close at shore depths, at water depths of around 2 to 5 meters in fairly sheltered metocean conditions. These wind farms could be constructed on dredged platforms to further reduce cost of nearshore piling construction. The power could be distributed through offshore or nearshore substations, depending on the requirements of the consumer. Although not considered for the economic case, excess power could be stored and converted for hydrogen if required. This slide provides an indicative economic case for such an offshore wind farm in this region. As shown over here, an indicative capital expenditure cost of around 1.3 million US dollars per megawatt hour per megawatt has been assumed, with a continuing OPEX cost of around 50,000 US dollars per year. An approximate power supply rate has been assumed based on current prices in Saudi. And based on this analysis, as you can see from the chart on the right, it was found that the straight payback period is approximately 14 years. Please note that it's a simple assessment, not considering any discounting of cash flows or equity debt considerations or any complex financial modeling. Although there's a potential for capex reduction through economies of scale or lowering overall costs, the simple payback is not going to be economically exciting for anybody. However, and as mentioned previously, the key here is not the economic case, but an overall objective of meeting net zero targets for the region. And offshore wind, as I said at the start, is one of the tools that can contribute to this. So just to finish off, in summary, we've been easily dismissive of the case for offshore wind in the past and the specific context of Arabian Gulf region, and for very valid reasons too. And I've discussed some of those. However, net zero could drive the dynamic in some places, in some specific locations in the Gulf, specifically considering the relatively low cost in shallow nearshore and benign metocean conditions, located in close proximity to high energy consumption centers. There is the additional benefits of consultants, contractors, fabrication contractors, subsea cabling contractors already present in the region who have extensive understanding and experience built up over many years to develop very cost-effective solutions. Therefore, it's an onus on us, all of us, to, when we engage with our clients, that this should be part of our discussions and discuss the potential of offshore wind regularly in our conversations with them. Thank you very much, and I'll look forward to receiving your comments or any questions you might have later. Thank you.
Thank you so much, Yasser. I think what I can say is that personally know some of the projects that are being conceptualized today in the Middle East region for offshore wind. So yes, it validates whatever you have shown in your slides. Thank you so much. Now, just to optimize the time here, what I would like to do, we still have got some time in hand. Maybe we would open the floor for question and answers for the first three speakers. We have some time, few questions, and I have the micro here, which can be passed around. So I would request the three speakers to come on the dais. Do we have any questions, please, for the speakers, for the first three speakers? Yes, on the back.
Thank you all for really informative talks. I will not conceal that my question is influenced to a very substantial degree by the fact that the area in Greece where my family resides has just seen their second once in a millennium flood in 3 years. And I was wondering whether in view of such phenomena that become more and more, frequent. I remember back in America when New Orleans was flooded fully by Hurricane Katrina. This was thought of something, rare or something. And now we seem to have one such event every year. I am wondering whether it is incumbent on us in academia to actually initiate a change of attitude on about what we are talking here, and instill what I would call a little bit of creative panic. That means I heard very nicely the economic arguments that went with the CCUS talk. But I wonder, has humanity realized what Professor Vega very eloquently has shown that, we keep missing and missing and missing targets. And the consequences has already started showing, and we should factor it in our whatever economics. Thank you very much.
Professor.
Thank you. Thank you very much, Professor Dimitri, for this question. Actually, one of the slides that I was missing is a figure with some photos of disasters, like the one that you mentioned, and also the fires. And we need to touch the heart of the people to really see that this is something we have to do and it's ours. But this is a huge campaign. I mean, we talk to my students, some of them are here. They are very much conscious of that, but don't turn off the air conditioner because I need it, correct? And then this is part of it because this is the electricity is associated to the climate change, etc., etc., etc. So what is clear is that we need a punishment if we don't do what we have to do. Humanity is like this. So the policies should really come and they should really force us to do this. This is, I give you one data. So for example, with Paris Agreement, now COP28, the countries talk and talk, but then they are not really pushing us to do things. There is no punishment if we don't do it. In the Montreal Protocol, it was the opposite. The Montreal Protocol was related to the emissions of the fluorinated compounds, especially CFC into the atmosphere, and they were banned. We could not use these compounds anymore because of the hole in the ozone layer. So because of that, we were forced to look for other refrigerants, and we did. Because it was banned, we could not produce that. So in this particular case, nothing is banned. This is, we have to, let's do it, let's reach 1.5. Then this is where we really need to convince us that we have to do things. My point really is also lose. If there is no money behind that, people will not do that. So it's not that CO2 capture is difficult, it's that it's expensive. Why should I capture CO2 if no one forces me to capture CO2? So in Europe, for example, now you have to pay carbon credits, and that is making CO2 capture more affordable, because you would prefer to capture CO2 if you know what to do with it than doing nothing and emitting the CO2 and paying the taxes. So we really need to be forced. That's number one. Number two, for the companies, and that's what we are talking about here, we need to see an opportunity, which means the companies need to change their mentality as well. So this is not business as usual. This is not business as usual. You can do it today, you will see the consequences tomorrow. So let's talk about wind offshore. This is an excellent thing where we really have to work to improve that. And the third one is the people, the young generations, correct? And us. We need to be convinced that this is in our hands. It could be in the hands of the politicians. It could be in the hands of the companies, but it's in the hands of each of us. And this is why the International Energy Agency put these behavioral changes as one of the things we have to look. So I touched the conscience of everyone of here. What are we doing to mitigate climate change? We, individuals. Also, what do we do in our research? What do we do in our groups? What do we do in our companies? But first, what do we do? Because if we don't start by ourselves, we are not going to accomplish this, which is a challenge, individual and global. Greece is a very bad example, but we have many others, correct? Very recent examples. So please think that we need to do something, and it's in our hands. With this, let's see what the others want to say, something else.
Well, I think I'd just like to add that as an industry, as a collective of industry and academia, we are in the business of solving problems. We're very good at it. That's where I think most people in this room have built a career out of doing, is solving problems, technical challenges. Now, we've more or less solved most of the challenges associated with all of these different topics, whether it's offshore wind, CCUS, hydrogen. We're a long way down the road in terms of solving those problems, but there's a cost to it. It's expensive. So now I really think it's around the global government collective coming together to work out a uniform carbon pricing mechanism to allow us as an industry and academia collective to accelerate the projects that we've already got in the pipeline. It's just economically they don't work. And that's why it's important that we lobby at events like COP28, and it's important that those events take place. And I think this year will be particularly important around pressing that agenda on trying to advance and accelerate the technology and expertise that we in this industry already have to make those climate change goals achievable. So that's from my side.
Don't have much to add. Thank you very much for covering pretty much all of it. I think when we just have these conversations with the clients, I mean, especially us in the consultancy industry or as academics, I think we just need to reframe the question. And I think that communication is really important. And we need to have this regularly with them. And I think more and more it's becoming acceptable to talk about, including some of these things. And I think we should continue to have those conversations.
I would just elaborate on Riley's comment, would be just extending that support from the regulatory authorities or the governments, not only for carbon pricing mechanism, but also for the wind or the hydrogen that, the ecosystem that is being built. Industry is ready, but yes, the support from the governments, the push from the governments is required in these sectors as well. Any other question?
Hi, good morning. Graham from Motive. Thanks for the informative presentations. They were really good. Good to see us talking about offshore wind. I think a few of us here who are involved in the offshore industry would argue that there's not enough wind offshore to put some turbines up. Quite a few of us have got multiple delays offshore with wind issues. I'm just wondering then, based on the last comments, what is government policy at the moment in the GCC and the MENA region as a whole around these technologies and bringing incentives to investors to invest in this product. I know that a lot of GCC companies invest in these products overseas, but based on what we've seen here, are there incentives for them to invest here? Thanks.
I don't know if I know how to answer this specifically, but I can tell you that the UAE is pushing very hard for the net zero strategy. This is clear, and we are open to any possibility to help us with this. That's why we just launched the hydrogen strategy, for example, that is very much related to renewable energy as well. And then we launched, I think we were the first GCC country actually with a net zero strategy as well. So the net zero strategy is based on different pillars, which are very similar to the ones that I mentioned today. So energy efficiency, renewables, hydrogen, etc. How much the government is really helping, I really don't know. But that the government is pushing and that we have very clear in the UAE that you need different technologies to accomplish this, and the doors are open to anyone bringing the technologies. This is very clear.
So I think it's a slightly different scenario in the GCC countries, especially more the more developed GCC countries. Most of the investment coming for these sorts of projects comes from the government. It's not private investor led like we see in Europe or the US. So the regulatory frameworks around some of these technologies are a little bit behind, but it's because there isn't such a high volume of private investment coming in to develop these projects. So I think the market dynamics in this part of the world are slightly different from that perspective. But we still need to get a mix of that private investment in. And when you talk about financing the energy transition, it all comes from that private investment. So in terms of trying to scale, that regulatory framework will need to be in place, and it is happening. I know that the UAE has already got some sort of a framework in place around some of these technologies, but again, because of the non-need for that private investment to advance projects, it's not on the top of their list. They're just going for the projects and being market leaders, early deployment of technology, early adopters, and it's really seen as a proving ground for some of these technologies to be deployed in other parts of the world where that private investment does sit. Anything to add?
Yeah, I don't know anything specifically about incentives, but I mean, what we see in the market is, for example, Oman is investing a lot of effort into, potentially using some of these evolving technologies as creating a market for ammonia, for example. There's a lot of projects coming out of Oman. They would like to capture a big share of the ammonia market, where the renewable energy that's generated in Oman is one of the lowest, with one of the lowest levelized cost of hydrogen. So there is definitely incentives for the governments in terms of capturing some of these emerging markets. And as I said during the presentation, I think it really depends on a project-specific conversation that you need to have with your clients, and I think that's really important, where you can communicate the exact value that incorporating some of these tools can provide value to the overall project. Thank you.
Just to add, as Rally said before, we are here to solve problems, no? So if you come with a solution to one of the problems, the way to work around how to bring it here is much easier if there is if you see there is a clear solution. And usually, actually, no one company. Usually, you need to have two companies that work together to deliver this. This is just an appreciation from what I have seen here for several years.
Thank you. We will now take a pause, a 15-minute coffee break, which will give us time to exchange ideas, exchange views again while we sip our coffees. And we come back again after 15 minutes in this hall, and we have another 3 sets of presentations to be covered, followed by the Q&A. Thank you so much. See you shortly. Yeah, I think we'll get going in the interest of time. The next speaker with us, he is online. Unfortunately, he could not join us in person due to his family reasons, I would say. I mean, but those are good reasons. He is joining us live online from Kenya. I'll just introduce the speaker, Carl De Winters from Hy-Energie. Carl has been involved in solar business in the Middle East since 2008, making him an early pioneer in this field. Carl has a vast experience in the regions with exposure to almost all segments of solar industry over the course of his career as solar promoter, leading an EPC company, a designer, author, and developer. Currently, he is focusing on enabling the energy transition to a green, clean economy with a special interest towards diesel replacement and innovative technologies like floating solar. Prior to this, he was active as sales manager, floating PV, and advisor to the chairman of the Phelan Energy Group, a South African developer leading the floating PV business development activities of the group worldwide. Graduated in Brussels, Belgium, with a Bachelor in Commercial and Financial Services, Carl also carries a Master's in Marketing from the renowned Welrick School for Management in Ghent, as well as a Master in International Politics from the University of Antwerp. Over to you, Carl.
Hello, and thank you for having me and allowing me to provide you this perspective of floating PV, maybe reintroducing this new technology into the MENA region, because not much has been done in the MENA region around floating PV. Also, thanks for the organizers for having us on this interesting event. Let me share with you what we're going to talk about today. I will introduce to you what is floating PV, or in a more common name called photovoltaics. We'll talk about the segments that are there, the forecasts, what are the PV systems installed so far, what are the advantages, and then we'll go into a little bit of detail on a particular interest of mine by co-locating it. We'll study about MENA, and we'll take you also offshore with a venture from Holland called SolarDuck. So let me start off. What is floating PV? Basically, we call this the third pillar of the PV industry, next to first pillar being the ground mount solar systems, second pillar being the rooftop. Now we also have a third pillar that will realize this vast growth in the solar industry, which is floating PV. It basically refers to solar power plants that are installed floating on an inland water body or an offshore water body, right? And it has actually enormous potential. If you would just study the addition of solar to man-made water bodies, then you could reach 4 terawatt of capacity. So that is really a massive amount of capacity that is currently not very much tapped. It's also a very versatile tool to kill 2 birds with 1 stone, one being water security and a second energy security. Specifically for floating PV, what is making it different from the conventional solar is that it is installed with adjustable anchors to accommodate for water level variations. But it's also important to know that floating is a very quick win, because it can be built in a much faster pace than what you would build on an onshore environment. And I'd like to draw your little attention to that engine, I call it, that I have put up on the top right, where basically floating PV systems provide shading to water, which prevent evaporation. It gives cooling to the panels, which is in the Middle East one of the major loss factors of solar, and that then reaches increased generation of the solar system. So what does the market look like? There was a market study by IHS Markit in 2022, which forecast that the floating market would reach close to 14 gigawatt by 2026. And that is mainly dominated by the Southeast Asian countries. You can see that on the little graph on the right. If you take the top 5 countries, you would notice that 75% of what is being built or planned is happening in India, Indonesia, South Korea, China, and Vietnam. It's also important to segment floating PV. You cannot put everything under one banner. And on the left, you see those 4 segments, which actually work in different degrees of difficulty. So the easiest and currently very common way to build in countries as Japan, Europe, US, is to build on ponds and lakes where you have very little wave action, not too much wind interaction. So very easy, very straightforward to build. Not a very deep anchoring system is required. You can even anchor from shore. A second segment is the segment of the reservoirs, where you could have face up to 2-meter wave height. So we're talking here hydro dam reservoirs and so on. A third is where we are working in areas that you call near shore, maybe in a sheltered bay or in a dock of a harbor that is sheltered from the element or from the ocean waves or the sea waves. And then the fourth level, which is very new, and I'll come to that in the end of my presentation, is when you really go offshore. And of course, then you have the full exposure to the elements, the salt, mists, the wind, oceans, storms. So that is the last segment, which is the most difficult one to address. Solar systems installed, floating PV systems installed. I'll show you some picture of that. Currently, we are over 5 gigawatt of floating PV systems installed worldwide, and it's growing very fast. In the MENA region, not much has been happened. It's quite new on this area, but on the top left, you can see here in Abu Dhabi, or where you are in Abu Dhabi, at Nouria Island, there was a hybrid system built, which was basically to offset diesel consumption from that island with an onshore solar site and also a floating PV system to complement that, because there was simply not enough space on the island itself. Some other pictures that you see on the top right is one of the first trials in Portugal, Alqueva Dam. Portugal is really one of the leading countries in Europe bringing this technology to market. Bottom left, you can see a nice example of where you have greenhouses, obviously large space constraints. So if you put those out on the ponds, you can save quite some space. And on the third one on the bottom, you see my favorite floating PV project, which is in Habcheon Dam in South Korea, which actually became a tourist attraction. They built floating PV systems in the shape of flowers, making it very aesthetic. Here you see some more views of sheltered in a harbor, and on the top right, even in Canada, where you have freezing conditions, floating PV systems can be deployed. So what are the advantages of the floating PV systems? There are quite a lot, but the main ones are, of course, that you have a dual utility of the surface area. So the underutilized water areas and existing infrastructure get used twice. You use the water for maybe water irrigation ponds, and at the same time generate electricity from it. Second, as I alluded to it, it prevents evaporation of finite water resources, something that I think we should really value in the MENA region, because our evaporation can reach very high levels. Third, we do not use valuable land, which can be used for other applications like real estate development or agriculture applications. Fourth is maybe surprising, but something, again, we should value in the Middle East, because one of our biggest losses, of course, are the loss of performance due to heat. However, if we can build floating over water, floating PV systems over water, then this cooling effect of the water can increase the performance up to 16%. And that's something that I think investors would probably value, even though that the floating PV system has a slight capex cost that is higher than the ground mount systems. And of course, it also reduces soiling, because by working over water, you have less impact of soiling, so the cleaning cycles can be extended a bit. And that's actually the second largest loss factor of solar systems in the Middle East, the loss of yield due to soiling. It also prevents the growth of algae, so the water quality of water is higher. provide shade for fish. And as I mentioned also earlier, it's quite fast to deploy, faster than working on a ground mount surface. And I'd like to draw a little bit of attention to this co-location of floating PV and hydropower. For me, this is really a non-brainer. As you will see, most of the advantages are the same as I mentioned before. However, there are two that I would like to put in the limelight. One being that if you combine a floating PV system on an existing hydro dam where you have existing infrastructure, then you can generate your electrical requirements during the day from the solar system, basically delaying your dispatch of water during a nighttime, and in doing so, shifting your use of water and therefore creating a virtual battery. And in doing so, you can resolve one of the big issues that we face in the renewable world, which is how do we get to low-cost storage? Now, by putting floating PV combined with hydro, we have that low-cost storage. And also, hydro dams have a function to play in drought protection. That is done by management of the water. Now, if we add on the floating PV, you have this additional dial of how to control that. So again, that is something that is very much valued in municipalities by managing that factor. And on the top, as you can see, if municipalities or governments engage in PPAs or in private-public partnerships, then such systems can be built at the low cost. There's basically no capex. The system basically pays for itself by doing this. Again, we see Southeast Asia as a leading area. Thailand has a large program for converting quite a lot of their hydro plants to co-located systems. Here you see a list of some of these quite large systems set up. China, of course, leading, although I have to say that China did not build it as a floating system, but as a combination of a fixed ground mount with a hydro setup to try out this technology. The largest one we see here is in India, Omkareshwar reservoirs, where 600 megawatt floating is currently installed. And I mentioned also Portugal. It's a leading country in Europe for deploying this technology. My current employer, Masdar, has commissioned also 145 megawatt in Indonesia. And then you see also other large systems coming up. Now, concerning the Middle East, we had done a study ranking which countries would benefit most from this technology, and this is based on a couple of priority criteria that we have put up. Obviously, high GHI. GHI means the solar irradiance that you have on the surface, so the solar power that hits the surface of the Earth. Whether hydropower with reservoir is available, whether the land price is high, because that's often a big driver for floating, whether there's a water saving potential, a large population, whether solar is already ingrained in the psyche or in the country itself, so it doesn't need much explaining, whether funding is available, and so on. And then we came to this ranking that you can see on the left with it's our ranking, of course, open for debate, but we put Turkey on the number one spot, Morocco, Iran, KSA, Egypt, UAE, Israel, Iraq, and so on. Again, I allude to this little engine, what I call the floating PV engine, where the shading prevents evaporation, provides cooling, increases generation. It's a very nice engine where you can see that if you work with nature instead of against nature, it actually brings you additional benefits. Now let's look into a couple of country profiles. We've taken here Iraq. This is a country study for Iraq on floating PV. Only ranked number 8 on our list. But if you look into detail at Iraq, you will find that they have 37 dams in the country, 5 of which are major hydroelectric power stations with almost 2.4 gigawatt of generation capacity. The evaporation from the waters in Iraq reaches up to 0.8 billion cubic meters per year, every year. And also Iraq is plagued by not a lot of water flows into Iraq. Often it is being diverted or used before it flows through the country. So water scarcity is really an issue. However, floating PV can provide there a solution, and up to 80% of the evaporation can be avoided. Just to give you a number, in the Middle East, studies have shown that per square meter of water that is covered by a floating PV system, 3 to 4 cubic meters per year can be prevented from evaporation. Of course, this evaporation, as you know, is caused by the high solar irradiance. In Iraq, it's close to 2,000 kilowatt hours per square meters. And also Iraq has an issue on generation capacity. They have a peak of 30 gigawatt, only 20 gigawatt is currently installed. However, they have put up a target to reach 33% by 2030 from renewables. And so solar could potentially account for a 12 gigawatt capacity. How it's a large, it's a difficult road to climb, because it would mean 1.7 gigawatt of solar capacity needs to be built every year for the next 7 years. And that's something you will find actually in a lot of countries where these targets are set, and then it is a very steep climb to reach that. Current capacity only 200 megawatt installed. Now, specifically for Iraq, if we look at the top 5 dams, this listing that you see there, total of 2.4 gigawatt of solar capacity could be achieved, which would generate 3.6 terawatt hours each year, every year for the next 20 years, and would save close to 80 million cubic meters of water from evaporation, which is quite significant in the big scheme of things. Yeah. Here you see a picture of those dams. Often they are very large water bodies, 20, 30, 40 square kilometers of area. So the floating system that is installed would not even take that much space from that water body. The second study we've done for the country of Morocco. Morocco is a country with quite a lot of dams, over 139 dams and additional 57 under construction. They have a major issue on water scarcity also, because the groundwaters that are being pumped out for irrigation for the agriculture are not getting replenished. So there is quite some loss from those dams, which amounts to 70 million cubic meters per year. As I mentioned there, we could avoid that by deploying floating PV systems. Again, Morocco has a very high irradiance, more than Iraq even, at 2,123. They have also set their targets. They're also having a very long road ahead of them, because on solar PV, only 200 megawatt is installed. If they want to reach their target of 20%, that also means 0.2 gigawatt per year would need to be deployed for that. So it's a very steep project timeline. However, if we study for the top 5 dams, a total of 1.2 gigawatt of solar can be achieved, reaching almost 2 terawatt hours of electricity, and would save 38 million cubic meters of water from evaporation. So as you can see, that's almost half of what is currently being lost from evaporation, just by not covering areas of those dams with floating PV. And we'll dive into a specific potential project at Al Wahda Dam, where if the project would go through, then 5.7 million cubic meters of water loss could be avoided, which represent almost 8% of the country's annual loss. Here is a picture. As you can see, this dam is the reservoir is covering a massive area. On the bottom left, phase 1, you see a 10 megawatt pilot built close to the dam, close to the existing infrastructure, so with low connection cost. And on the phase 2, if you would extend that with 240 megawatt, you can see the area of what it takes from the reservoir surface is really not that much. It's basically also providing this dam with this additional storage capacity for dispatching power to the surrounding areas. Good, now let's dive on something which is this 4th segment, what I mentioned, when you go really offshore. There's a company in Holland, the Netherlands, called SolarDAC, quite innovative and recently formed, spin-off from Shipyard, which is focusing on pure offshore floating systems. And this is, of course, fueled by the strong macro trends that we've seen, the growth of renewable energy power demand, the fact that solar is critical to meet this increased demand, because of course we're building a lot of solar, but also the demand is increasing almost faster than by the rate that we can build it. So IEA had made a study showing that if you want to be on track by 2050, we would need annual capacities of solar to reach 630 gigawatt by 2030. Currently, we're close to 200 gigawatts per year that's being built. So still a factor 3 to be increased. It was also brought up by one of the previous speakers that most of the population is in coastal areas. So that's also something that is helping the development of floating PV, offshore PV. And then, of course, floating is offering this new frontier, basically creating a new asset class that can be explored. SolarDuck has therefore developed this innovative model where you basically have modular units that click together into building these offshore solar plants. They're robust, they're scalable, they're quite easy to install, they're efficient on the O&M because of the concentration that you have, and they have a minimal impact on the environment, barely take up any space of the ocean bodies, of course. One nut still to crack is the competitive LCOE. That will come by increasing the scale of that, since it's still an early phase company. Here they shared with us a view of their pipeline, which reaches 3.3 gigawatt. But you can see that the company was formed in 2020. Only 2 years back, a full-scale demonstrator was launched, and a big milestone was that the large utility, German utility RWE, engaged with them in a partnership for launching now a 0.5 megawatt demonstrator in the North Sea. This will continue, this development, so we're following this very closely. It's one of the most innovative ways of bringing solar to the offshore areas, and you could think of coupling these platforms with existing wind power infrastructure, and then sharing this infrastructure over the two technologies. This is a view of their pipeline that they have, that they're currently working on. I think Japan, as being one of the leading countries, the first moving countries in floating PV, is also engaging on this. And closer to home, we have also in Qatar some studies going on to see how that can be deployed. Good, so I'd like to leave you finally with share some of my favorites aunt's Flemish wisdom. She mentioned to me once that there's people that see things happen, and there are people that make things happen, and there are people that sometimes get a whack over the head and say, what did just happen? So I hope that we all can engage on these new technologies and actually make it happen. Thank you very much for your attention.
Thank you, Carl. Thanks for your insights on the floating PV and where it can be deployed. I would like to now invite Ian Crossland from Motion. Ian is an accomplished and results-oriented C-level business executive with 15 years of experience directing overall aspects of technology development and commercialization within oil and gas sector, and most recently moved into the renewable sector as part of the energy transition with Motion Energy. He has spent the last 12 years within SMEs technology companies, mainly to develop and deploy disruptive technologies to highly conservative and forward-thinking end users. Prior to this, Ian spent his earlier part of his career with Schlumberger, which is SLB now, working both domestically and internationally, covering well site operations, R&D, and various management positions. Ian, welcome on the dais.
Can everybody hear me okay? Yeah, that's really good. Yeah, I'm a little bit taller than probably the average mic, so apologies for that. So hopefully you can hear me okay when I go through my presentation here. Great, excellent, really good level of presentations we've seen so far. I'm hopefully going to give you a little bit of different flavor onto something else in terms of renewable energy. First and foremost, let me thank the SUT for this opportunity to come here to speak. and also from the Khalifa University for actually hosting the event. It's a really nice place to be, and excited to be here. Is that better? Yeah, much better. Okay. Yeah, apologies. I'm 6'3", so maybe the mic, you know, it's. I think they have the same problems within these sort of events. Okay, great. Yeah, I'm going to give you a bit of different flavor in terms of wave technology as we go through this next 20-25 minutes or so. Motion Energy. Yeah, founded in 2015, as you can see. We like to see ourselves as the kind of the second generation of technology, building on past and commercial technical experiences. To date, we've raised over 13 million in terms of investment, of which 80% of that comes through public supported funding, which is great. You can see on the background there, you can see the picture in 2021 where we launched our first prototype. And that was given to us, you know, through a competitive procurement program, which we were very successful in getting to that position. We're 23 industry leaders, soon to be about 26. We've got some more positions coming up, which is great. Key thing here, about 8 nationalities. So we're very fond of that, actually, in terms of having that diversification. And we have a Scottish heritage, as you can see. So I'll get into the next slide here. So I'm just going to give you a brief short history about wave technology itself. From the origins, surprisingly, wave research development has a long history. Compared to what we're seeing today, we're still a newbies on the market, I guess, from that perspective. But in the UK, it started around the 1970s in Edinburgh, which really was the epicenter and fulcrum of actually developing wave technology. So looking at the top right here, it started with the Duck Array. This was from a famous inventor, which was in the wave sphere, called Stephen Saltire from Edinburgh, which is also the birthplace for motion. Over time, R&D efforts have had a series of highs and lows, and many of you might be aware of some of these pictures I'm sharing with you on the screen today. After a promising start in the 70s and into the 80s, the nuclear industry really emerged and took over as the wave energy. So in that time frame, we took a bit of a back seat in terms of technology and development. In the 2000s, it really started to emerge again, industrial focus within startup within the European Marine Energy Centre back in 2003, and it's now celebrating its 20-year service history. So really a good place for taking the technology, developing it. So this is where we tested our first machine in 2021, the Blue X. So as you can see, during the 2000s, it really started to transcend with some big names and companies into the sector, like companies like Polaris. You can see the picture there on the bottom right, which is the Sea Snake, and then Aquamarine came about to gain a lot of traction. Unfortunately, both of those companies had big ambitions to build at utility-size scale machines. But if we take the machine of the Polaris, which is actually a 1,000-ton machine and cost tens of millions of pounds, they developed at pace, which was really, I guess, their undoing it a little bit in terms of unable to be able to de-risk the technology fully at that time frame. But sadly, those companies I mentioned came to administration in 2014, which was a shame. And ultimately, that was the same time when we saw effectively what was the worst down cycle in the oil and gas industry. So again, timing is everything in terms of technology as well. Moving on into the industry, we merged with the Wave Energy Scotland programme. This is the programme that Motion was involved in. We got provided funding support to develop through what we call a competitive bid programme, and we successfully navigated that to build the first of the kind prototype that you see on the previous slide. So we consider ourselves a second generation wave technology company, and we're taking the lessons learned that we've developed over the past and taking a different approach. So start small, where you can actually devolve and actually get the technology to a point where it's actually commercially viable, and then go big later. And that is our approach. So Motion's approach that we take, you can see here, what we look at is we optimize, we validate and deploy. And this really is about kind of embedded into our expertise. So we have, I'll just click on here, as you can see, hopefully. Yep, great. So we use simulation as our in-house software modeling, and it's a foundry piece of the technology that we have within the company. So we're able to simulate different geometry parameters for a given location or resource. We then use AI optimization, and we're using based algorithms to capture the best effectively outcome for structural mass, whereby mass is actually a proxy for cost, for example. Once we get the numerical optima, then we embody that into the physical model. We use the scaled down actual size of it, and then we test it in the wave tank testing facilities you can see on the bottom right there, demonstrating here, which incidentally is about 100 meters from our facility in Edinburgh. Excuse me. On this graph here, you can see here, we can demonstrate the impact of optimization process. It's really important, actually. And we compare a standard tubular hole floating hinge raft compared to what we have with the Blue X. What we're showing is the power capture per mass of the device on the vertical axis. Okay, and on the horizontal axis, we have the wavelength or period of waves. So introducing a sloped section called wave channels and some asymmetry into the holes. If we look at the blue line, we're able to push the peak significantly higher, increasing the bandwidth of response and in addition. So really fundamentally, you can see almost maybe eight times more power relative to what something without this actual optimization being adopted or implemented into in terms of when we go through the design process. And I guess this is critically important for islanded or off-grid applications, whereby we're looking to provide a baseline level for power continuously. So just a few quick ones on the fundamentals. So how does our wave energy converter work? So if we look at the operating principles, so we have, as we mentioned, a floating asymmetric raft. We have two hulls which pitch relative to each other. And inside that, we have a generator. You can see maybe on the center here. Oh, excuse me. Do we have, and right in the center here, you can see where the generator is in between the two holes. And that pitching movement actually drives the generator, which produces the power, which we then send to an umbilical and whatever it's connected to from that point onwards. Three design drivers to consider is the length of the device, which determines the length of the wave we can capture. Submerged volume is related to the amount of power that can be produced, and then the steel plate, which drives the fatigue life, of course, and integrity of the structure. Power absorption is mentioned, i.e. geometry is helping us to capture more energy for a given wavelength without the use of clever control systems. By designing the machine actually produces much more power, then you optimize that with control systems inboard. We have a slight mooring system that also simplifies the setup. So we're depth agnostic, so we can deploy it in 1500 meter water depths as equally as we can deploy it in 20 meters or 40, 50 meter water depths as well. And you'll see this actually on the video shortly. I'm going to show you, and it can handle a device of range of what I would call abilities, so survivability, reliability, repeatability, which is really important part of what we're trying to demonstrate in multiple different wave conditions. Finally, the track record, we've been demonstrating through stringent testing, integrating with partners. I'm going to show you an example of what that integrating with partners looks like to demonstrate the commercial readiness of the product itself. Deployability and potential. So when we consider deployability and where we can deploy around the globe, there are a number of considerations. Not all of them are considered at this point, but there are a number we take into consideration. Two, for example, is power potential and survivability. So on the graph on the right-hand side here, or the main graph here, you can see in the center, you see the capacity factor. So how much power can be available from a 20 kilowatt rated machine. So our first commercial machine is the 20 kilowatt rated machine. And give you an example, that can handle, let's say, power requirements for a 4 to 8 well subsea tieback, for example. And then the graph on the right-hand side here at the top right shows a scatter diagram over a period of time and what sort of waves we could get in terms of, or power from waves we can in terms of significant height and period. And then what we look at then, we replace what we call the worst case 100 return period contour around the plot. And then we test the machine at that seas at scale and check the survival parameters. Really important part of the process when we're looking at where the system can be deployed in what environment. For example, we want to check the machine hull. So for example, when you have these super large waves, you want to make sure the machine doesn't actually come back and hit the hulls hitting itself. So it's really important to understand, what the conditions are of the wave converter is going to be involved in. As you can also see in the wind sector, we have what we call cut-in and cut-off conditions. However, in wave, it's much more two-dimensional. We have to consider the wind, but also a wide range of conditions. So that's not easy to find. So in the case, you can think there's a significant wave height and period. So we consider this as steepness, and we cover a wide range of operational envelopes in terms of it. So it's very broad for us. I guess a lot of the 80-20 rule you can apply to that. The key thing about the technology is it automatically, using itself in terms of passively can disconnect the PTO, which drives, a lot amount of the forces that you would see on the wave converter when it's going over these waves, and you can see it. But ultimately, when it comes to these worst case conditions, it can passively disconnect itself. So if we look at the Blue X, so the Blue X is our prototype, and we're going commercial with this product itself. It was accumulation of a competitive pre-competitive procurement program, run by Wave Energy Scotland. So we tested our machine in 2021. So we awarded an actual contract to build the prototype. You can see on the picture here, and we can see the Blue Wave machine itself. So this was in a test facility back in 2021. You can see, as I mentioned, it's 2 hulls that rotate about the hinge, which drives a generator. The testing went on for 4 months at sea, and we basically we weren't connected to anything at that point in time. We just wanted to take the validation of the equipment. Since then, I'll show you, we have a project ongoing where we are connected to a piece of equipment. So those waves we can see here, we have another one around about 2.1 meters significant wave height. So by design, the machine dives through the waves itself, much like a surfer would go out from the breakwater. It actually dives through the waves, so protecting it, and so we don't have this kind of slamming load where you would see with a vessel, where it comes over the top of the wave and then it crests. By design, it's meant to dive through the wave itself, so you can see all the green water, blue water coming over the top of the machine. By design, it's meant to do that. So the Renewables for Subsea Power project. This is one of the projects I was mentioning. It's a really, really important project about how we talk about collaboration and bringing different partners into the industry to understand how we can provide a technology for decarbonisation focus. So this is what we call a flagship project within the Net Zero Technology Centre in the UK. It's a first of a kind full-scale system providing power and communications offshore. And we did this, a lot of the testing last year onshore, and then we deployed it offshore in February of this year. It initially was a 4-month project, but we've extended it now up to nearly 12 months, and we're able to do that by bringing in other partners. So along the bottom of the screen here, you can see companies like Harbour Energy, Serica Energy, PTTEP, Baker Hughes, ourselves, Volum, and Transmart, all contributing to this project itself to deliver, a standalone ecosystem for power and communications, but also powering an AUV. Or, for example, here with Baker Hughes, we have a SemStar 5, which is a subsea controls module, where we're powering that. So from the top, you can see the Wave Energy Converter. This is really the communications gateway. This connects to the subsea battery management and storage system provided by Volum. The bottom left of the infographic, you can see the AUV has a docking station, so it is resident, where we can then send it out to do flybys and things like that during the testing program. And further on the right here, you can see Baker Hughes, the SemStar 5. So what we're trying to show here is that you can actually open and control subsea modules and controls from that position here. It's about 3.5 nautical miles offshore from Orkney. It's about 50 to 53 meter water depth. So it's quite analogous to sort of shallow water operations. And we're demonstrating, as I mentioned, remote communications, control and monitoring. The qualification program, we should hopefully get to TRL 6 by the APA standard by the time we finish the testing program. What it aims to do in terms of boost confidence. So this is an industry thing. It's not just about, motion. It's our particular Wave Energy Converter. It's not about, the tier 1 companies like Baker Hughes. What we're trying to do is bring this technology together. We can deploy it from an industry perspective, which is really, really important to demonstrate, and try to sort of pave the way to wider carbon mitigation. In terms of applications, this is really important. I can talk a lot about these different applications, but one thing I noticed today in terms of the talks, and in particular, is around CCS. This is something that, certainly for us, is a big focus, certainly in the midterm, where we can provide a full, power electric communication systems to that subsea asset, whether it be existing, retrofitting, or whether it be a new one. The other key thing about that, we talked about this, how do we do the monitoring aspect? So as you can see in the previous example, we had an AUV. So again, monitoring the subsea bed in terms of any potential breakthroughs and things like that is also an important part of the system that could be provided. So meta-ocean data, leak detection is really a key thing, and CCS, but you know, one of the key things we're talking to all our customers is about this umbilical remediation. Every single operator around the globe has stranded wells. That's fact, due to whether it's issues with IR, communications. So the application to deploy this technology to reinstate those wells, meaning potentially that they wouldn't have to go out there and drill new wells in terms from a carbon perspective, has a huge value. So we're very focused on talking to a lot of these operators about how we can reestablish those wells and get them back online again. And of course, the cost comparative to go out drilling new wells is order of magnitude. So one of the things, you know, try to think about is, you know, how this technology can help decarbonize and developments and enable electrification. You know, this is a really important part of what we're trying to do here today. So very quickly, some of the highlights. So we have, you can see from the picture here, you know, this was deployed. I guess I'm just going to talk a little bit about the solar aspect. This has been one of the key learnings for us. We talked about, you know, combining technologies, renewable energy sources together. And I think that's a key indicator, and certainly one of the key learnings that we've had. As you can see from the bottom right here, we have some solar panels on the deck. So very small, around about 500 watts on each on the forward hull and 2 on the back hull. It's been a big key learning. One of the things we noticed actually during the period we've been testing is the solar contribution provides at least 200% of the comms requirement for this system. So 100% of that potentially can be exportable down to whatever we're connected to, which is a key thing to understand as well. So utilizing those periods where the wave technology or the wave energy potential is not so high, you can actually extract from the solar and utilize that as well. So when you start to aggregate those up, you know, you can actually double them up. It's quite significant. This is an example. This was just very quickly. This was around about a 5-meter significant wave height. So really tough environment. One thing to remember is the stability of the machine. So there's not much pitch and roll, which is really important because obviously you have the antenna, and the antenna is the gateway or communication gateway to the subsea equipment below. So very stable within its environment. Very quickly, I just want to show you just a little bit in terms of the video here. You can see this was the subsea battery pack system that was stored on the seabed, and this was the AUV. So we've done something like about 50 docks, undocks from the AUV. Been very successful. And it's got something like 6 HD cameras. It has the 4K capabilities in terms of video. And you can see here where it's docking in and out of its docking station. So we're going to continue to do that into what further part of the testing that we got ongoing, which will take us through to February of this year. But you can see how easy it is for the docking station. It's a pinless connection, so it has the capability of recharging and then going out and do additional mission runs, coming back, uploading the information back through up to the wave energy converter where we transmit it back to shore. In terms of battery stabilization, excuse me, sorry, yep. Let's go back there. So the key drivers here is the ability to have powered, you know, stored and available on demand here, really important. So understanding the end duty cycles use, power requirements, asset shutdowns, planned or unplanned, startups, operation and maintenance, environment, contingencies, for example, will help us understand to clearly sizing the system to account for these operating parameters. So the graph on the left shows the power generated for a given period of wave performance month by month, for example, and on the right shows the power available via battery storage. What we've been learning is how to best utilize the learnings to optimize the power potential and to streamline that process. So i.e. harvest that energy at the best time and replenish the power that is drawn down the battery during the testing program. And try to make it a much more elegant system, because what everybody's looking for is that uninterrupted power supply and reduce the intermittency, which is really important. And we're using things like AI learning, for example, artificial learning and forecasting models in terms of when the wave power generation is best to harvest and when we can best then switch the machine on or switch it off to reduce the O&M operational cycles of the equipment. So I just want to talk a little bit about this power hybridization. We talked a little bit about it today as well in terms of combining renewable energy, and I think this is a really key important part. On the top right, you'll see some. Sorry, on the top left, you see some. We have an array of solar panels, as I mentioned. We have 2 on the forward hull and 2 on the rear one, which is about 500 watts. And what we noticed that during the RSP project, there's some amazing results that can only sustain the comms, as I mentioned, but we can also use this energy to export to the battery system or whatever we're connected to, thus improving the power export and reducing those intermittencies during the low wave power generation periods, which we know many parts of the world has that environment. And then we have to figure out, well, how we're potentially going to get that or replenish that power that battery storage has been taken or drawing from. So for example, by 10 o'clock, we observed that the batteries were full on board of the wave energy converter, and that potential energy that can be exported could be sent down into a commercial opportunity, for example, which we're looking at doing. So by scaling this array on the decks, and we have quite a lot of real estate on top of the wave energy converter to put, something like maybe 3 kilowatts, maybe 4 kilowatts of additional sort of solar panels on top. If we start to aggregate up there, that would give us much more power that we could deliver actually to the end use. And that's really important in those regions where both can be harvested, potentially reducing intermittency. So for example, here in the graph, you can see the both. On the right-hand side, you can see what we call the blue star, and this is a graph that we can show how much potential energy can be generated. And we have the example for the Arabian Gulf. We have the one for where the RSP located in the North Sea, and in Sardinia. So for those periods, you can see month by month, you can see the wave energy, which is in the blue, and then the solar, which is in the red. If we start then aggregating those up, the potential is even higher in terms of power export, but also reduces that, periods where low wave energy actually it could be, challenging to actually replenish the energy. We'd have to look at alternatives where we'd have to go out and maybe put that back into the system. So look at these models. We've compared it and done some experiments in Orkney, and we have an engineering doctorate that's been looking at this. And with the errors that we're seeing, we found to be less than 2%. So we're very, very focused on trying to see how this can potentially be from a commercial application. So I mentioned earlier in my presentation, start small, go big. This is really important in terms of how we were successful as a company and where we go from here. So start small, and we go from the tens of kilowatts on the left-hand side here, focused on kind of DC tiebacks, subsea wells, residential robotics, marine awareness, really important. And then we start scaling up to the hundreds of kilowatts. One of the key things, we announced last week, Offshore Europe, we just won a 3.8 million euro award from the EU. That's to go towards developing the next size of the machine, which is really important. And then that will be a natural progression as we go up to the megawatt size scale. One of the key things that we fundamentally believe that coupling marine renewable energies with other energy sources, and we've seen this examples with the previous presenters today, really helps with intermittency. So you can imagine, these wind turbines, there are something like 1 to 2 kilometers in between them. If you start talking like the really large ones, all of that real estate could be potentially infilled with wave energy converters, solar power, solar panels, and things like that, which can then be obviously exported down the same export line. The thing about it is that you have, the period where the waves are generated, the period where the wind's generated, and where the solar are. They're all out of sequence with each other. So having those potential energy sources all coming together reduces that intermittency, which we're all trying to achieve. And of course, is part of the roadmap going down there. So, and one of the key other things to mention as well is, the previous presenters mentioned in recent awards back in the UK in terms of renewable energies, wind actually wasn't awarded anything in terms of fixed platform wind, let's say, for example. One of the key things was that the tidal actually was awarded 5 times more than the planned award was probably going to give it. So it's interesting that from an ocean energy perspective, there's a huge focus now on how we can deliver that with the technology that's coming available quite soon. The other key thing to mention, I deal with these all the time, is that a lot of the super majors, I'm not sure if you're aware, but they're all establishing companies like Total, companies like Shell, companies like Hy-Energie, all have marine renewable energy departments where they're creating to help put together technologies that can help with this decarbonisation focus. And beyond that, as they all look for diversification in their energy mix, they're looking for technologies that can help do that with their short and mid-term and long-term goals, what they have as well in terms of those aspirations. So with that, concluding remarks, yeah, really important. I think wave energy has a significant role to play, certainly in the North Sea and certainly in other parts of the world. And I think it's hopefully it's going to be exciting to see that. Collaboration, I don't think there is a collaborative project going on right now. I can demonstrate all of this, particularly within the sort of our region and with the customers that we're dealing with. Larger scale decarbonisation opportunities await, that's for sure. Islanded power systems is really important. You know, CCS, hydrogen, we can provide power. What you ultimately do with it is really your decisions. But the fact is we can provide power, we can provide stable power in terms of supporting with subsea battery storage and energy management, which is also important. As I mentioned, we've delivered the system to the renewable subsea power project. We're working with some really good collaborative partners on that. And of course, then we've just been awarded another grant, so to help develop that next size machine by 2025, which is really important. So again, energy mix, trying to understand how that, each part of these different options can come together to a common goal. Yeah, and getting momentum and seeing towards the industry traction. So, we've got international investment. We're just going to be signing 2 energy super majors into this project as well, which is great. We just recently got assigned with PTTP from Thailand, for example. In the Gulf of Thailand, they have a very similar type of decarbonisation focus as well. So it's an interesting project to be in. So with that, I will leave you guys and thank you for listening. And I'll take any questions as we go to the close. Thanks.
Probably it's better to use this microphone for me as well. And thank you, Ian. I think for me, 3 takeaways, key takeaways from Ian's presentation. One is the resilience. In your initial slides, you never gave up since you started. Collaboration, joint industry participation is key to the development of new technologies, innovations, to make these projects happen. And third is the scalability, make these projects at scale to make them commercially viable at the end of the day. And of course, I would say the fourth one goes with, if we need to accelerate, we need a lot of support from the authorities, the governments, the regulatory framework, etc. With this, we come to the last session of the day, the last presentation, which is Subsea 7's presentation. It will be run by Suranjan Govinder and myself. I will be supporting for a couple of slides in the beginning. Suranjan is a graduate. I'll just first put the slides. Okay, so coming back to the introductions, Suranjan Govinder is a graduate from the University of KZN, South Africa, and currently working as Subsea 7's engineering manager. Suranjan has more than 16 years of installation engineering experience in the offshore industry. He has spent most of his career out of Singapore and is now based in the UAE, looking after regional engineering function for Africa, Middle East, and Caspian region for Subsea 7. Myself, I am Ashish, and I am the energy transition lead for Subsea 7 for Africa, Middle East, and Caspian region. I'm also based in the UAE. And I've been with Subsea 7 for 5 years now, and over 15 years in the energy industry, now more so in the renewables. Now, as I said earlier, Professor Vega kind of helped in terms of understanding and outlining earlier the hydrogen value chain, which is the hydrogen production, the various ways in which the hydrogen can be produced, and then related to the transportation and then the utilization. She also alluded us to the fact that hydrogen is going to be one of the key energy mix in the coming future. And she rightly said, we are not there yet, but it is now we have to work on the technology development in order to support the overall hydrogen ecosystem. So that's what our presentation today is all about, is Subsea 7's view on how the offshore side of hydrogen in terms of the facilities infrastructure can be incorporated in the mix to make the hydrogen projects possible. So this gives the perspective why we are talking about only offshore from Subsea 7's perspective. This is the world we live in today. As the world continues to evolve, Subsea 7 has primarily been an offshore engineering and project management contractor, facility integrator. We continue working in the lower carbon oil and gas, the traditional oil and gas, but with a different perspective of lowering the carbon footprints, electrifying the systems that are currently existing and the new ones that are being built. The second one is carbon capture, utilization and storage. This is other segment that we are active in, specifically the offshore CCUS side of thing. The third one, fixed and floating wind. Subsea 7 has been doing the fixed floating wind for a decade or so now. And then lastly, the theme for this presentation, the hydrogen. So Subsea 7 today is building the enabling technologies and the infrastructure to make the offshore hydrogen projects possible. So taking the last section out of these 4 segments that we work in, offshore hydrogen ecosystem. Let's talk about what is involved in an offshore hydrogen ecosystem. It's the green hydrogen production, first of all. Now, there are various ways of producing green hydrogen offshore. It could be through offshore wind installations, decentralized offshore wind installations, where you have the hydrogen production systems, which is electrolyzers, as Professor Vega earlier explained, as one of the methods of producing green hydrogen, to be installed on the facilities itself, on the platforms itself, and produce hydrogen. Or it could be the large-scale hydrogen production systems like FHPU, floating hydrogen production units. We all know about, we all are accustomed to the oil and gas industry. We know FPSOs, floating production system units. So these are similar to those systems, but for the hydrogen. So these are the centralized hydrogen production systems, which could be used for generating the green hydrogen. The next segment is the transportation. Now, the transportation could be through the various pipelines that we are already using in the oil and gas industry, but with a different view now in terms of modifying the technology, the material composition to cater for the different set of molecules now, which is the hydrogen. So the technology exists, which is transferable with certain modifications in the metallurgy of these pipelines. The third one is the storage. The storage could be for when we generate the hydrogen offshore, whether it's centralized or decentralized. So it could be stored at site, or the storage could also happen at the port area. Now, when we talk about the net zero being announced by a lot of countries, so there are a lot of port clusters that are getting involved in that mix, and they are looking at the decarbonization strategies. There is the entire marine sector right now looking at decarbonization. A lot of vessels are being converted to run on the low carbon fuels, including hydrogen. So they would need the bunkering in near future for the hydrogen. So how the hydrogen could be stored closer to the ports to cater for the marine sector in future. So this is what we believe that from Subsea 7's perspective, when we talk about the hydrogen ecosystem, from generation to utilization, this is where we fit in from the offshore perspective. Now, I think this slide talks about why are we looking as Subsea 7 in this sector. Now, the first and foremost point is that a lot of technologies that already exists in the oil and gas industry and the skill sets that already exist in the oil and gas industry could be transferable to this market, which is the hydrogen, offshore hydrogen. So today we have a unique position in terms of what we have been doing in the oil and gas industry for last 5 decades or so, developing technologies, developing skill sets, delivering complex projects across various regions, offshore projects across various regions, and also collaborating through the industry. What we are also looking at, which other speakers also mentioned, is that we are also looking at how to reduce the LCOH, which is levelized cost of hydrogen production. Now, that can only be achieved by technology development, collaborations within the industry, and also producing hydrogen at scale. So for the next set of slides, I will hand over to Suranjan. He will take us through the various archetypes that Subsea 7 is conceptualizing today and working on towards developing the entire green hydrogen offshore ecosystem.
Thanks, Ashish, for the introduction. Thanks, everyone, for being here. Don't want to lose the momentum, so I'll just jump straight into what Ashish was mentioning in the previous slide on the energy system integration. So taking that a bit further, let's look at the concepts that can be used for hydrogen production. We'll start with basic four archetypes, which are looked at by Subsea 7. We'll start with archetype number 1 on your top left. So this is basically point-to-point transportation. Onshore hydrogen is produced, transported via subsea pipelines to another onshore facility. Thereafter, it could be either utilized or distributed as required. In terms of the subsea pipeline portion, there's obviously inherent complexities involved here and some challenges, which I'll touch on a bit later. But this could be either utilizing already existing subsea pipelines, which are found suitable for hydrogen production, or alternatively coming up with a new network, new pipelines that are laid specifically for hydrogen transportation. The second archetype looks at having a dedicated offshore infrastructure for hydrogen production. Here with this archetype, we could split it into two possibilities. The first one on your left, on your bottom left, is more focused on off-grid floating production systems offshore, which are integrated with offshore wind. Either floating or wind is also a possibility, and together with subsea hydrogen storage systems. The clean hydrogen then produced is then exported to onshore via export or infill lines. Another alternative at the top for archetype 2 is having decentralized wind facilities, which are integrated with hydrogen capture units. Here again, the clean hydrogen produced is then transported via export or infill lines to the onshore facilities for further use. For archetype 3, this looks at hydrogen and electricity generation, more to optimize the revenue of power production. You could use centralized or decentralized, again, methods, transport, and with the transportation facilities for both hydrogen and carbon as and electricity as shown. Another option here is to integrate this with the onshore grid for electricity, so it can be utilized during the peak loading on the electrical systems onshore. Moving to the bottom right, the fourth archetype, or the final one that we are looking at, is a small-scale production just to cover domestic use. So here again, this could be two possibilities that are being explored. The first one being, just skip to this. The first one being decarbonization of existing either platforms or assets or facilities. The hydrogen is then integrated for buffer storage with your subsea storage systems, or it could be used as fuel to service vessels that are hydrogen friendly in field. What Ashish was discussing a bit earlier in terms of port integration production with buffer storage, This ecosystem obviously involves a lot of collaboration with the ports, also with the vessels offshore for them to be hydrogen friendly to accept fuels, hydrogen fuel as required. So before I proceed to the next slide, I mean, this is by no means an exhaustive list of archetypes or concepts or possibilities. This is just what Subsea 7 is focusing on. The main driver for focusing on these is that this is where our core area of expertise lies and where we think that we can add the most value into the system. Of course, it also requires us to collaborate with other industry partners. So linking up these concepts with what's in the market today in terms of clients and the drivers that need to be in place in order for making these archetypes a possibility. Respectively, for archetype number 1, offshore pipeline transportation of hydrogen. So here your typical clients will be gas grid operators. Here the needs or the drivers that need to be in place to implement this will be pipeline systems for transportation of hydrogen, gas or derivatives, and multi-nation cooperation and investment. For archetype number 2, dedicated offshore facilities to produce hydrogen. Typical clients, power producers, tech gas providers, and oil and gas clients. The drivers here that need to be in place is having offshore wind facilities that are optimized for hydrogen, preferably being off-grid and independent. Archetype number 3, hydrogen and electricity to optimize revenue or meet the variable demand. Similar in terms of clients who will be attracted to this archetype as archetype number 2, power producers, tech and gas producers. With this archetype, a little bit more is required in terms of infrastructure to be in place. So you look at offshore wind facilities, pipelines, cables, electrical and gas infrastructure, and also looking at how to improve the utilization of the plant to benefit from H2 curtailment, wind of market volatility. Archetype number 4, small scale production for local or domestic use. This will probably attract more industries that are dedicated, that are wanting dedicated supplies for such as ports, which we discussed earlier, transport and off-grid customers. Here, the demands will be local production driven by demand or resource opportunity. Also, customers that are focused on decarbonization of their assets. So based on the last 2 slides, it may seem like, concepts that are in the distant future, but as Professor Vega said, the future is here and now, and there's significant work ongoing. There's collaborations in place already that are looking at the studies to put this technology in place. So in this slide, we focus more on what Subsea 7 is, who and which business associates Subsea 7 is collaborating with. But I think it's important to mention that this is not only, there's a lot of others doing similar collaborations in the industry, and that's what's required for all of us to move forward to achieve the goal of the challenges we are facing today. So on your top left, you look at the collaboration we have with H2 Shore, hydrogen coastal storage and distribution. This is for the Port of Aberdeen. Here we're just looking at options and possibilities for onshore storage along the coastline across the Port of Aberdeen. This study and techno-commercial study kicked off around June this year. The collaboration with OneSubsea, also, I think this one kicked off around June this year as well. This looks at more large-scale floating hydrogen production offshore in Scotland, and the MOU was signed in June. Yeah. ENBU, a German company, focusing more on fixed wind platforms. So here the challenge that we have, of course, is having these hydrogen production units integrated into offshore platforms, or offshore wind platforms rather. So the studies here are ongoing to look at how best to integrate these two systems. And this one, the study for this, also the MOU was signed in May as well. Another industry collaboration is Air Liquide. With Air Liquide, we are also doing a similar study for fixed wind architecture. And this study also kicked off in May. So I think the important point to look at here is, with all these collaborations, we are trying to address the gaps that we have at the moment with the technology. We are trying to contribute what we have and go to industry partners that are experts in their field. So apart from what we've shown here, we've also in discussions at the early stage with clients, planning with clients who are looking at the hydrogen export line across the Mediterranean, connecting the Middle East, West Africa, and Europe. So that's still at the early stage of discussions. And with regards to all the bodies below, IRENA, Alliance for Industry Decarbonization, EPRG, nothing's impossible without involving various industry bodies from an advocacy, policy, and a regulatory point of view. So these are collaborations and global associations that we are proud of. So technology development through industry collaboration is what we are basically looking at, and what many of the other speakers have mentioned also. So over the last 5 decades, Subsea 7 has developed technologies in the traditional oil and gas portfolio. A lot of these technologies, such as water treatment, pressure management, power controls management, and materials technology, can be directly transferred as knowledge into hydrogen production. Of course, there are different challenges with hydrogen, which we need to address, and that needs to be done through a collaborative system. So I keep mentioning about the challenges. So one of course, the major challenges that we have, particularly for offshore pipeline transportation, is hydrogen embrittlement. There's a few studies that's been done within our pipeline group in Subsea 7, which looks at the effects of pressure and temperature on hydrogen embrittlement. In effect, this leads to increased fatigue cracks, which are generated, which ultimately reduces the life of the line. It also results in reduction in fracture toughness and ductility. So here again, the wells are most susceptible, particularly for offshore pipelines, due to the welding system that's used. The different microstructures that are introduced into the system because of the welding process, metallurgical defects, which inevitably will be there with offshore welding, and stress distribution during the lay of the pipeline. So at the bottom, various collaborations and initiatives to tackle on this subject. H2 Pipe, which is a joint industry project by DNV. Hydrogen pipelines by EPRG. With hydrogen, particularly for offshore installation, there's no spec, so to speak, as yet. So these studies will definitely form the basis for the specs that are going to be rolled out. So here we are taking a novel approach to offshore hydrogen storage, looking at compact, modular, and scalable subsea module. So this is one of the patents that are pending by Subsea 7, which is Powerbox H. So here, These are individual modules or units which allow for subsea storage of around 15 tons of gaseous hydrogen at up to 350 bar at a range of water depth up to 1,500 meters. What that translates to in terms of power storage capacity is around 500 megawatt hours per unit. Of course, there's also the option of linking up multiple modules to increase the capacity of storage. With this design, here again, it's clear that a lot of the technology we already have can be transferred, and this is a good example. We are utilizing mature components, nothing specifically dedicated for this particular unit. So we have very compact, easy to manufacture units using composite cylinder tanks, which are not difficult to find, type 4 PE liner and fiber wrapping. Which also reduces the need for maintenance and also the effect of corrosion. The other benefit on the right here, which is mentioned, is it's a shore-based assembly. So all the testing can be done onshore at the facility where it's manufactured before it's installed offshore. From an installation point of view, the benefits here is that instead of relying on a craned vessel to lift and install, we can have a floating and a structure that is towed out to the intended installation site. And then using an integrated ballasting system, it can be deployed to the intended location. Another benefit with that would be that if we need to relocate this, we could deballast the system and then relocate the box. Qualification tests were performed at Sintef Ocean in Norway and witnessed by DNV. So this is inclusive of the whole towing and installation process to get an idea of the loads that are going to be applied environmentally onto the system. Right. So onto my last slide, just key messages and takeaways. The more I hear all the other speakers, you realize that actually we all have the similar messages in terms of collaboration within the industry in order to get things rolling a bit faster. So offshore wind is a significant part already of what we do, and we are focused more on the wider energy transition. So developing field development solutions and technology development to enable offshore hydrogen production is in essence what we are all doing. Collaboration and partnerships are essential to how we operate. Here again, common message through all the presentations. And through collaborative work, technology and system integration, we contribute to a lower LCOH to enable large-scale offshore hydrogen. Again, back to what Ashish was mentioning on scalability in order for the cost to be lowered. All right, thanks everyone for your time.
So we have a question at the back.
Great, thank you. My name is Agis Giaralis. I'm with Khalifa University in the Department of Civil Infrastructure and Environmental Engineering. Part of EU Coast Action funded international collaboration. We are partners with coming from more than 30 countries, and we are looking into modular energy islands, floating islands, and trying to combine obviously tidal, wind, solar, wave energy. We had our second annual meeting last week in Istanbul. Putting aside wind and tidal, our concept looks similar to what Mr. De Winter was showing, like hexagonal or octagonal modules hinged together with solar panels, as well as we try to think of producing energy from waves using live hinging. So since we have, I guess I cannot help but questioning the two experts we have here in floating solar and wind and wave. How doable is our idea? I mean, what would be the top two challenges you would think of when you think of combining, let's say, floating solar and wave
Okay, so I mean, this goes back to the integration of all the systems together. And I think Ian touched on it in terms of this is the challenge. This is exactly what the challenge is, getting all these systems to talk together and work effectively together, because every system has certain benefits at different timings. This is definitely going to be the area that we need to focus on. I think the only way to get things moving on this is through collaboration, because no single party has all the solutions for it. So I mean, it's a good question, and I think it's definitely a relevant question.
I think one of the other key things as well is how to integrate them all together. I mean, using, for example, when we talk about floating offshore wind and wave, utilizing the same mooring systems, utilizing the same infrastructure is actually one of the key things that we're trying to address. And there's a lot of development in that area as well, is how we can combine infrastructure that ultimately helps with the levelized cost of energy in terms of cost. It's really important is how we can combine that. I mean, the key thing is, I think, trying to understand what energy mixes work best in what environment. You might have a combination of floating offshore wind and solar. It could be another ones that potentially with wave and wind would be the most cost benefit economical way of actually putting a network distribution together. So understanding that, and I think one of the other key things I think for us is that available to access to funds. So innovation funding is also important. I mean, there's a lot of technology developers like ourselves who are on the point of being that pre-commercialization, and we then need to step up now to get them into the environment where they're designed to be operating to at pace. This is the challenge, and when we talk about at pace, it's ramping up quickly, particularly within the renewables, within the sort of the marine renewable energy. At pace means they wanted to actually distribute it something similar to seeing without floating offshore wind and wind historically. The challenge is that that's been developing for years and years, and yet we're expected to go do this at pace, but we can't do it alone. There needs to be innovation funding, there needs to be investment, there needs to be those early adopters. I think that's one of the key things for us that we need to get across the line. And I think with collaborative projects that we're involved in, that actually helps, bring home the message. And as I mentioned, getting the sort of the energy super majors involved in the projects, because then they can see the pathway, segue into that larger scale technologies, I think is important. The other key thing is, I think there's a lot of development as well as about having the capability to switching between different energy sources. So there's a lot of focus right now on capabilities of when to harvest that energy from whatever it's coming from and at what time. I think that's also important, and there's a lot of development in that area as well. So I think it's accumulation of bringing on all these technologies together at pace, and that will help us then, meet some of these demands that we're trying to facilitate. Because we know we're behind the curve, that's fact. But how then do we expedite it at pace quicker?
Carl, would you like to also, support the perspective?
Yes, I think I'm very much in line with what was said. It will be driven economically. For example, you have to look at also what you are replacing. Yeah? Say, for example, you want to decarbonize islands. Currently, they are shipping in boatloads of diesel at $2-3 a liter. That obviously gives an opportunity to provide alternative solutions that may be out of the starting blocks having a higher capex or a higher operating cost. However, many of these technologies are not moving at the same speed. If you're looking at offshore solar, as I showed in my presentation, it's quite young. It's a few years that we're experimenting, having trials done. And of course, as you know, solar is supposed to last 20-25 years. So it's even though it can technically be done, you would not be very happy as an investor if that system is only surviving for 5 or 7 years. That will not make your business case. So we're still early at that phase. But that being said, integrating these different technologies together, working with nature instead of against nature, and unifying all the experts to bring it on the similar platform will definitely reap a lot of benefits. There are a lot of common costs that can be shared between the different technologies to make a very attractive business case.
Thank you, Carl. Any other question? Yes, left.
Thank you very much. My name is Abdulatif. I'm a PhD student in the Chemical and Petroleum Engineering Department. My question is for the team that showed hydrogen storage, subsea hydrogen storage, in which you are storing hydrogen in an artificial vessel. I'm wondering, do you have a collaboration with the team that store hydrogen underground reservoirs, underground hydrogen storage? Thank you.
Yeah, with this regard, we have not had any collaborations or studies to look at underground hydrogen storage as yet. You are quite right. I mean, it's the artificial system that we have in place above the seabed, basically, that we have.
Okay, thank you.
Hi, I'm Talia Sherrod from Fugro. We work for a geodata company, and we have a lot of technology that we operate in different parts of the world in terms of collecting geodata. One of the biggest challenges that we face when we start bringing technology from other parts of the world, which is very successful, to the Middle East and North Africa region, is the temperature. We've talked a lot about different technologies here, particularly the solar I'm referring to. Do you see temperature being a potential barrier of, new innovation coming to this part of the world?
This is a good point, and we see it even now in terms of assets being mobilized from other parts of the region, Europe into Middle East and Africa, and even from an asset point of view, there are teething problems with that transition. So yes, it would be something that needs to be looked at. I wouldn't say it's a showstopper item that will stop us from progressing. Definitely, I mean, those will be some problems that we'll need to find solutions for.
I can maybe just comment maybe on battery storage and things like that in terms of temperature. I think, battery storage is a key part of what we're trying to achieve. And, it certainly is much more positioned better to be subsea. There's a huge amount of benefits from that perspective, from the battery technology, but also from the utilizing battery technology and storage on an asset where you're actually taking up space. So from that perspective, it would be great. I mean, from the solar perspective, we did quite a lot of testing with different types of solar panels with our machine back in 2021, and we went to a specific type of brand that we're using on the machine today. Yet to be resolved, I think, in terms of if it's going to be affected by bringing to this environment here in terms of the temperature, but certainly from not probably Carl's more suited to answer that question there, but certainly from what we've seen, the temperature is actually, the solar panels work very, very well in the environment, in the water itself, much better actually than being on land where we did comparative testing in 2021.
Carl, please, your perspective.
Yes, there's in fact one of the points I brought up, right, on the floating PV, that you have this cooling effect of the water, and temperature is onshore the largest yield killer of a solar system, next to the dust. So floating PV systems do address that point, and I'm glad to hear that in practice you can actually see this this gain that is helping to increase the yield. Now on the technology itself of solar, remember my early days of solar 14 years back. Solar panel was the same whether you put it in Norway on the Sahara Desert. These times have evolved. These days there are panels being developed for desert regions, N-type panels, dual glass, half-cut cells, multiple busbar. Many of these technologies are finding its way into a segment specifically for our region also. So there's definitely innovation going on, but I would say it's already there.
Time for one last. Hi, my name is Mohammed Fadil. I just started my master's in chemical engineering over here. I have a little bit of experience in offshore, so this question is for Subsea 7. One of the archetypes that you were talking about where there was shore-based hydrogen storage for fueling vessels, offshore vessels. I mean, like it's very little experience that I have from offshore, but from my experience, it was like these vessels being very dependent on thousands of gallons of heavy diesel and all.
So how close is that marine industry, these vessels in particular, to being transitioned into being dependent on these, like hydrogen, for example?
Yeah, so good question, but from a subsea 7 point of view, just in terms of what we are doing at the moment, so we do have a vision for, I think it's 2030, which is to have certain vessels in our fleet dependent on hydrogen. So the wheels are in motion towards that direction. I don't think we are far away with that. But here again, I think it's going to be a question of scalability. So you need a number of vessels in different fleets in different companies to be dependent on hydrogen in order to make it economically viable. So here again, I think the economy is going to be the driver of it, but the technology, I think, is almost there.
Let me just add to this, Suranjan. So I was in a marine and shipping conference arranged by Norwegian Embassy last week in Abu Dhabi, and in one of the panel discussions from Maersk Supply. So the gentleman mentioned that 1.5 year ago, they had one vessel operating on a low carbon fuel, ammonia, and within a span of, I think it was, he mentioned, since then they have 32 vessels converted to run on the low carbon fuels. So it's already happening in the industry. And when Maersk is saying we believe the others are also looking at the same kind of pace, and it's just the port infrastructure needs to be developed and ready at the same time. When these vessels are out there, they should be able to be fueled with that low carbon fuel. So it is happening, and that's part of one of the studies that we are currently doing with Suranjan mentioned with Port of Aberdeen. So it's production of green hydrogen in the nearshore area, and then storing it for the utilization as part of the decarbonization of port, and also used for the bunkering for the vessels that would run on hydrogen. So it's happening.
Thank you.
Thank you. And with this, we close the Q&A. I would now invite Adrian Philip to the podium to share his thoughts and give the vote of thanks. Thank you.
Hello.
Can everybody hear me? Okay. Well, first of all, what a fantastic opportunity to bring industry together with academia. I could think of no better subject, frankly, than to be discussing in this day and age than the whole renewable energy opportunity. And there's no question there are huge ambitions in the region for renewable energy. And I think even more interesting, perhaps, the G20, we just heard the announcement of a green energy transit corridor through the Middle East. And I think as a community, the SUT, and fundamentally we're about subsea technology, but it's also about the surface. We wanted to, and we're obviously delighted to host this event, and set out to examine, what the offshore industry and subsea marine industry is doing to contribute to the renewable energy mix. I was always curious to know, given the enormous wind energy developments around the world, whether there was an opportunity for this in the Middle East. Whilst it sounds like a tall order, and it's like, and the reason Carol's not here, by the way, and he's the only one who's had a proper excuse, is his wife is supposed to be having a baby, potentially either yesterday or today. So he's dialing in from Kenya, and we can only thank him for his contribution or his dedication to the cause. But we've heard the rationale for floating solar. It makes a lot of sense in hot countries when it comes to conserving energy, even efficiency for solar panels. And of course, when it comes to the wave energy side of things, I mean, who knows, in the more benign environments of the Gulf, whether that's a better environment for, the sort of mechanical mechanisms of the floating solar, just given the problems that they've had traditionally in just being torn apart by, the ambient conditions in the North Sea. So, who knows, that just might be a way to look forward. We're also seeing a lot of carbon dioxide. Well, the first carbon dioxide projects in some of the North Sea fields around Norway. And there's a lot of offshore fields, obviously, here in the UAE. And so, why wouldn't we, look at that as a potential place for carbon or certainly CO2 capture? And of course, we've seen the floating hydrogen concept. What's wrong with moving floating hydrogen facilities around the Gulf to generate hydrogen where it's needed? But my own view on renewable energy, particularly solar, is of course the costs are coming down. I mean, the sorts of costs we're seeing per kilowatt hour generated energy are absolutely phenomenal. And whilst the costs of wind have also come down, we're starting to see those costs going back up again. Because reliability is a big issue, and I think people are just starting to recognise what it takes to make wind work offshore. And also the other factor that the wind industry tends to share a similar supply chain to the offshore oil and gas industry. So we're seeing those costs going up. Of course, not to mention the other issues with cost of capital, and that's not the same across all of the regions around the world. And I guess the basic fundamental issue with wind and solar is that the sun doesn't shine all day, and the wind certainly doesn't blow. So these are fundamental issues that need to be resolved. We've obviously seen volatility in the gas price recently through either COVID effects or Ukraine war, but it's still efficient, it's cheap, it's abundant as a source of heat, and there's still plenty of gas here in the region. We've seen the latest offshore round of wind tenders in the UK suspended with no bidders, which was interesting, and that in many ways is because the cost of offshore wind has gone up. And whilst we know it's the right thing to do, the cost of capital is higher. It's not, well, certainly in some parts of the world. And the other thing we're not factoring into the cost equation is the staggering cost of increasing the size of the worldwide energy grids to deal with the additional electricity or just transporting all these electrons around the world. We also know there are political and other vested interests in the renewable energy space. And I've actually had my own experience of this developing solar here in the region, just up against local regulators and local utility companies who just don't really want to see their, breakfast and lunch eaten by renewable energy companies. So this is back to Lourdes' point, I suppose. This renewable energy transition can only really work, I suppose, we can find a mechanism to pass on the true costs of producing carbon with the associated energy source back to the consumer, because then people start to vote with their feet. So hopefully we find a way to shed some light on some of the possibilities offshore in the marine sector, and I hope that's been of use to everybody. As an organisation, the SUT sets out to inform and to bring people together and to generate these sorts of discussions. And what better time can we be doing this than before COP28? And on that point, I think Dr. Sultan Al Jaber is the right man for the job. Clearly, with ADNOC, Masdar, Mubadala behind him, is a huge amount of cash and potential investment behind them. And I suspect in many ways, as we've discussed, that's where the investment has to come. So I'd just like to take an opportunity to thank everyone for coming. It's really great to see you all here. I hope we can continue this discussion. I think it's a great opportunity, as I said, to bring academia together with the industry. Thank you very much for setting the scene, Lourdes. I think it's great just to sort of see the full sort of perspective. And then we've seen the various companies step through, the various options, whether it's wind, whether it's solar, whether it's carbon capture, hydrogen, and of course, wave generation. So I'd like to thank the speakers for doing a great job, particularly Ashish for putting together as the moderator. Our sponsors, which have been Worley, Motive, Motion, Subsea 7 and Xodus for some excellent presentations. And finally, I couldn't leave without a huge word of thanks to Khalifa University, Dr. Lourdes Vega for allowing us to come here, setting all this up for us. Vinod, who needs another special word of thanks in the background for finding a way to dial Carol into this conversation, and Alex, who's also in the box. And the final huge thanks is to Reem. Is Reem here somewhere? I just want to say thank you very much for all the help on the admin side, and we have a small gift for you if Leslie would like to come forward. And because I'm a bloke and forget all these things, Lourdes was kind enough to buy the flowers, so thank you very much, Reem. Okay, so I just finally want to say thank you very much. Safe travel, drive safely wherever you need to get to, and I hope you've enjoyed the session. We'll have a stand at ADIPEC for the SUT, so do come along and see us somewhere in the marine and logistics zone. I think Catherine's still there at the back. And see you next time. Thank you very much.